University, USA. He has 25 years of teaching experience. Because I know that he is also involved with four, committees of Department of Physics and Astrophysics, and he is going to, continue his talk on electromagnetic theory and the topic polarization today as well. So I welcome you, Dr. Sanjay, and I request you to continue your lecture, from where you left yesterday. Please start your presentation.
Thank you, Dr. Bindal. Thank you, Dr. Verma. And welcome to all the students who are part of this webinar. So I'll start with a little review of what we did yesterday and then proceed for today's lecture. Okay, so this is, yesterday we discussed polarization, and these are the four topics we decided to cover. Today we will continue with propagation of electromagnetic waves in anisotropic media, and then quickly go over propagation of light in uniaxial crystals, and then towards the end, very few optical devices, which are used in detecting polarized light. These are the three books which I had mentioned yesterday, from which I'm basically taking the referencing. So a lot of the diagrams and the overall approach is from these two books. Optics,
Dr. Sanjay?
Yes.
Dr. Sanjay, can you please adjust your webcam so that we can see your full face? Yeah, this is better.
Okay. Yeah.
Because in the video, it's been cut completely.
Yes, that's true. I'm also not tilting my...
Thank you so much. Thank you
so Eugene Hecht's book is a very readable book, and I will advise all undergraduates to go to have a look at it. And with Indian edition, it's not very expensive. But these days, even PDF version is available on the internet, so you can download and have a look at this book. Professor Ghatak's book is also extremely good, covers lots and lots of topics. Born and Wolf's book is a kind of treatise. It's very advanced, and it's more than 900 pages. But so it's meant for advanced level students and researchers. But certainly, there are certain topics which are accessible to undergraduate students and early postgraduate students. And what is very important about this book, like all very, very good textbooks, is that even though the language may appear terse, but the concepts are extremely clear. So one can very easily see that Max Born actually is a Nobel laureate. So these people have actually thought about intensely, very clearly what they're writing. So that's a kind of, very different book, kind of book this Principles of Optics is. So basically these three books are sufficient for the polarization topic at the level with which we are discussing. I don't know about whether Professor Ghatak's book is available in the PDF form, but Optics by Hecht and Prince Born and Wolf book, they are available on the internet in free PDF, so anybody can download. Now, proceeding about what we were discussing yesterday, I will quickly go through the important results. Okay, those are those things. So, first thing which we discussed was how do you represent a plane, represent polarized light. Okay? And the idea was that the EM waves are transverse, so there's a plane perpendicular to the direction of propagation, and in that plane you pick two orthogonal directions, just call them x and y directions, and the electric field in that plane would be sum of the components of the electric field along those directions. So that's how you can write down the field part around x axis, the field part around y axis, and the sum of the two. and instead of dealing with a monochromatic harmonic wave, so there's only a single frequency and corresponding wave number, and the function is a sine, or you could have taken sine or cosine. And what produces different polarization states are different amplitudes of the monochromatic harmonic wave along x and y axis, plus, and this is very important, a phase difference. Okay, so epsilon is the extra phase difference between these two components, and by picking different ratios for E0x, E0y, and the phase difference, one can create all different kinds of polarizations. So that was a basic representation of polarized light, which we started with and which we'll continue to use today also. And then the other thing which I would like you to keep in mind when we proceed for today's lecture is how we got the result about the relationship between dielectric displacement and electric field. Okay, so this was a relationship between definition, one can say, of electric displacement and electric field. And displacement, notice, is basically a sum of electric field plus the polarization. Polarization is the polarization here which is induced by an electric field in a medium. So any medium would have positive and negative charges. When there's an external electric field, that electric field displaces the center of positive and negative charges. That produces a dipole moment, and dipole moment per unit volume is the polarization. Okay. What is very important, when you separate the two charges, the dipole moment itself produces an electric field. So this electric field actually is a sum of two fields, the one produced by the external sources and also the one produced by the dipole moments themselves. Okay? But nevertheless, we define this quantity D, which appears in Maxwell's equations. We do not go into the details of how it comes, but this quantity D appears in Maxwell's equations. That's why it is important for us. And what we argued yesterday, that if the medium is anisotropic, P would not be parallel to E, which obviously means D also would not be parallel to E. Now, this is a very different condition than what you would have discussed in electrostatics, because in electrostatics, typically you deal with linear isotropic media. Now we are dealing with anisotropic media. So P is not parallel to E, and which means D is not parallel to E. And then we want to represent this relationship that there are two vectors, namely D and E. They depend upon E, but the two are not parallel. So what you can do, you can write down every component of D as a linear combination of components of E, and the coefficients and principles can be different. So you have three components of E for each component of D. So there'll be three components of D. You can think about 3 cross 3 matrix. So this permittivity tensor, which are made from the coefficients of this relationship, that would have 9 components. But then we argued that out of these 9 components, only 6 would be independent, and that comes from energy conservation. But furthermore, every anisotropic medium would have what is called asking people are welcome. So you basically, the energy conservation tells us that this permittivity tensor has to be symmetric. So the epsilon KL is equal to epsilon LK. That reduces to only 3 independent components. And another constraint which you get from the positive value of energy field density, field energy density, is that we can define our coordinate system such that it is oriented along what are called the principal planes of the crystal. Okay? When that happens, then things get even more simplified, that then there are only 3 dielectric constants which you have to worry about. Okay? So, so these are X, Y, Z are the principal plane directions. Principal planes, principal axis of the crystal. And if your coordinates are oriented along that direction, then out of those 9, only 3 independent, coordinates, three independent elements of the permutivity tensor remain, so you don't have to worry about any more elements. So this is something you have to keep in mind, the relationship between D and E when your coordinate system is aligned with the principal axis of the crystal. Now, if you proceed further, okay, now we continue with the propagation of E and M waves in anisotropic media. Okay, so let's again go back to a monochromatic wave, but the wave which is plane, which means the wavefronts are plane, and in our case, the earlier we had presented the wave is traveling in z-axis, but now let's it could be traveling in any direction. Okay, so this vector k now is basically a vector in 3 dimensions, some given vector in the 3-dimensional space. So this represents now a plane wave which is traveling in direction given by vector k. And we have used the complex representation. The idea is that one can use this complex representation, and you will see why we are using it, because it's extremely useful mathematically, this complex representation. But ultimately, when you have to compare with experiments, you take the real part of the complex things. So that's the thing which you have to keep into account. Ultimately, for comparison with experiments, for comparison with real fields, you have to take the real part. Okay? So anyway, so let's stick with this complex representation of electric field. Now what we have here is this with this exponential factor here, we can get a phase velocity, and phase velocity is the ratio of the angular velocity divided by the magnitude of the wave vector. Wave vector, remember, is magnitude is 2 pi by lambda. Okay? So that gives you basically, the speed at which the phase is traveling, and this phase basically means is that that's the speed at which wave fronts travel. Remember, wavefront is basically the locus of all the points on the space which have the same phase. So wavefronts of a plane wave would be plane surfaces, and these plane surfaces are traveling with the speed v, which we call the phase velocity. Okay? And the phase velocity is given with the ratio of the angular frequency to the magnitude of the wave vector. Now, since we are talking about the complex representation, this vector here, E0, that can also be complex. And that's very important for representing the polarization states. See, if E0 is a fixed, is a vector with only one component, or let's say a fixed vector, then it becomes a linearly polarized light. Okay? That is not very interesting, because that's only one kind of polarization. We want to deal with cases of all possible polarization, and that one can generate by letting this E0 vector also complex. Okay? What that means is that when you, okay, I'll come to that certain things later. So complex, then the different components of this E, they can have different phase. So this is what, for instance, I have written for the right circularly polarized light. So right circularly polarized light, if you remember from yesterday, was a combination of X component and Y component of the electric field, but there was a phase difference of pi by 2 between the two. Okay? We have the same component, X component, Y component, but the phase difference now we can introduce extra like this. Okay? So this makes this vector E here actually a complex, because it has a complex part. So this allows us then to represent all kinds of polarization states, if you let this E0, but because you can introduce different, phase difference between the two components, you can write down different amplitudes for the two components, and you can create any kind of polarization state. Other thing is that this, of course, phase is also constant, phase difference. So E0 is a constant factor. It does not depend on the position and the time. So position and time operators or differential operators will act only on the argument of the exponential function. And that is that leads to one of the great utility of this complex representation for the wave, because if you talk about differential operators of time and space on this wave, then their representation is very simple. In fact, the differential operators become algebraic operators. So if you have, del operator acting on that wave, okay, del, either del dot E or del cross E, for instance, all you have to do is that del operator will extract out an IK. And then you have the multiplication of the original function with that. Similarly, if you have del by del t, then del by del t operator will extract out a minus I omega. So differential operations do not change the function. All they do is they basically multiply those functions with these constant factors. That is the great utility of complex representation. And if you apply these things on Maxwell's equations, and the two Maxwell's equations are like these two, del cross E, which is the Faraday's law, and modified Ampere's law. Okay, we are not taking any free current here. Then, if you apply, del cross and del by del t on the fields, remember all the fields have that constant exponential factor, okay? Exponential ik dot r minus omega t. So what do you get? You get these equations. So Maxwell's equations for those plane waves, for those monochromatic waves, monochromatic plane waves with arbitrary polarization, they are basically now algebraic equations. Of course, they're complex, but that doesn't matter. They're algebraic equations, which means they're operate. Now we can manipulate these equations very, very easily. Okay? So that's a great utility of using complex representation for the waves. Now, what can you conclude by looking at these two equations? For instance, if you look at the first equation, is that B is proportional to K cross E. It means B is perpendicular to both K and E. Okay? And notice that when you say something is perpendicular to something else, then perpendicular is a mutual relation. Two vectors which are perpendicular are basically associated. Okay? Other thing is, if you look at this, D is perpendicular to K and B. Okay? Other way to look at it is that then we get it. B is perpendicular to electric field, that comes from here, and D is perpendicular to the magnetic field. So these relationships, these perpendicular, which vector is perpendicular to which vector, you can extract out that information by just looking at these two equations. Okay? Now, but something else we also have to think about what is going on. See, both B and D are perpendicular to K. And if you have any vector, K in this case is the propagation vector, the vector in direction in which the wave is traveling. Okay? If you have any vector, there would be a plane perpendicular to it. So what you're saying is vectors B and D are perpendicular. They are basically in the plane which is perpendicular to K. And further, B and D from these equations are also themselves perpendicular to each other. So now you can imagine what's happening. You have a vector K, okay? You have a vector K, and perpendicular to that vector is a plane. And in that plane, there are two other vectors, B and D, which are perpendicular to each other. So K, B, and D, they form what is called a orthogonal coordinate system, or orthogonal set of vectors, because all three are perpendicular to each other. Okay. Now this is important, which is different from what we have been, what you would have discussed, what you would have known from propagation of EM waves in isotropic media. Notice that you cannot say anything about the relationship of E to K. There's no equation which says that E is perpendicular to K. We have other relationships of perpendiculars, but E is not necessarily perpendicular to K. Furthermore, we know that for anisotropic, D and E are not parallel. Okay? So it tells us if D and E are not parallel, and there's no relationship in general which tells you E is perpendicular to K, E need not be perpendicular to K. Okay, so that's very important. So E need not be perpendicular to K. In fact, if you also notice the fact that D is perpendicular to, okay, now let's leave that out. Okay. So what we notice is that since E is not necessarily perpendicular to K, it means that it need not lie in the plane defined by B and D. Now, this can be seen from the following. Remember, there is a plane which contains B and D are perpendicular. We know E is not parallel to D, but E is also perpendicular to B. Now, in a plane, if you have two vectors which are perpendicular to each other, then naturally there's only one direction. If there's another vector which is not perpendicular to one of them, then that cannot be in that plane. So later I will show you a diagram how that happens. So keep in mind that E then is not contained in the plane containing B and D. There should have been a diagram which just a minute, maybe I missed something. Okay, I think I jumped the slides here. Oh no, it's all right. Okay, we'll come to that diagram in a moment. Okay. Now, what we are doing here is, remember there were two equations involving B and D. Let me go back to those equations that were on the previous slide. Okay, these two equations. So this has, equation of E, it has B, you write B in terms of, you can take, cross product of this equation. So you have K cross B coming here, and then you'll have, K cross B, you write in terms of D. So then you will get an equation involving D and E. And that equation is the one which was showing here. Now look at this equation carefully. Okay, you have D, you have some constant vector. Let's not pay attention to that. You have E vector. Then from the E vector, you're subtracting something. Now, what is this? This is basically projection of E along K, unit vector. A is a unit vector. And then you're multiplying that projection with the unit vector along K. So this is what we're showing here in this diagram. We have vector K. We have, some E in some direction. What we can do is we can break up E into two parts. One part would be so that then this E is sum of this vector and this vector. This vector is precisely the projection of E along K, then multiplied with the unit vector to get the vector. So this part is basically, which appears here, is basically this vector. So when you subtract this part from the vector E, all you're left is this. This is the part of E which is perpendicular to K. All right, you got it? So now let's see what is happening here. We had two vectors, K and E. Now any two vectors define a plane. So imagine this is the plane. The plane of the screen is the one which contains vectors E and vector K. Then what we do, we break up this vector E into two parts. The one part which is along K, other part which is perpendicular to K. Both these parts are in the same plane. Okay. Then what you notice from this equation is that vector D is basically constant times this vector. So important thing is that vector D lies in the plane defined by K and E. Okay, you got it? So this is what you get. So D is in the plane defined by K and D is perpendicular to K in this plane. That's what we can prove from this equation. Or we can do it the other way around. There is a plane defined by K and D because this is the direction of D. Okay? So there is a plane defined by K and D, and in that plane there is vector E. And E is not parallel to D because this is the direction of D and this is E. So we got this thing. K E is in the plane defined by K and vector D. So what you're doing is we're trying to get more handle on what is the direction of E. All right, so this is about, we'll draw a diagram in which, whatever we have figured out about the directions we will put together. For the moment, also look at other things. We discussed yesterday something called the pointing vector, which is basically cross product of E and B. Okay? with a constant with the permeability factor here. Okay. So vector pointing vector by definition is perpendicular to both E and B. Okay. Notice that K is not perpendicular to E, but S along which the energy flows, that is perpendicular to E. So obviously S and K would not be in the same direction. So that is again is an important thing. Energy flow and wave propagation are in different directions. Energy flow is perpendicular to E and B. And K is the direction of, and you can see very easily, I mean, if you have any direction which is perpendicular to E, that would be, in this plane, of course, it would be like this. That would not be along K. So a very important result for anisotropic media, then you get a physical result that energy propagation direction and the direction in which the wave is traveling, they are two different things. It's a kind of counterintuitive, but you have to keep this fact in mind that the two are in different directions. Now this is a diagram which encapsulates all the things which I discussed about different directions. So, and this can be drawn in different ways. This is the one. This is the diagram I have picked from Born and Wolf. So we have vector B, and notice that all the other vectors which I discussed so far, whether E or D, in this case, this is the direction of K, and this is the direction of pointing vector. So all the vectors, you can go back to the equation and convince yourself all the vectors are perpendicular to B. So all of them lie in the plane which is perpendicular to B. Now within that, we have two sets of vectors in that plane. One is formed by D and K. So D and K are perpendicular. Okay, these two are perpendicular. Other set is formed by S and E. S and E are also perpendicular to each other. And the angle between the two, whether you take D and E, or you take a vector K and S, the angle between them is the same, which we just call alpha. And that's the angle by which physically the wave propagation direction and the energy transfer difference are different in different directions. So keep this diagram in mind. And important physical fact is that energy transmission and wave propagation, they are in different directions, and that angle between them is the same as the angle between E and D. Now let's see. Now we know that the wave propagates at the speed of the phase velocity, omega divided by magnitude of vector. So that's the speed at which the wave fronts are moving. We have already seen that energy is not moving in the same direction. So naturally, we ask the question, what is the speed at which energy is transmitted? We know that energy is flowing in the direction of the pointing vector, which is perpendicular to both E and B, but at what speed? So that's what we want to figure out. So what we have here is, first of all, this is the energy density of the electromagnetic field. Yesterday, we had the similar relation, but you have half of E dot D and half of B dot H. But the two happens to be the same. That's why the factor of half has been used from one of the Maxwell's equations. And then we just did, move the things around. This is the triple scalar product, and E cross B is the pointing vector. So we got this result. This is the energy density, okay? And this is given by the dot product of K and S. And remember, K and S are not parallel. So there would be a cosine alpha angle coming from this dot product. Now, what we do is we define a quantity which you call ray velocity, which is different from phase velocity. Okay. What is ray velocity? We say, okay, this is something which is in the same direction as S, and its magnitude is Vp by cosine. Okay. Why you're doing it? Because what is K dot S? K dot S, remember K is a unit vector. So K dot S is basically magnitude of S times the cosine of angle between K and S, and that angle is alpha. So what we do then is the following. You can write vector, pointing vector is along the ray velocity, that's VR. But then you have here the energy density. Okay, just taking this thing around here, where VR magnitude is Vp divided by cosine. Now, what is the interpretation of this equation? Okay. Now, I would advise you to just imagine, I haven't drawn all the diagrams, but we can, just talk about that. And I'm sure that that will be not very difficult. Imagine, there is there is a cylinder, and that cylinder is of, length equal to the magnitude of VR. And that cylinder is along the pointing vector. And energy is like it's a flow. So whatever energy is contained in that cylinder, in 1 unit of time, that energy will flow out of one end of the cylinder. Imagine further that, that cylinder has a unit cross-section area. So then whatever energy crosses that flows out in unit time is basically magnitude is equal to the S, because that gives you the flow of energy per unit area per unit time. The energy which is flowing would be, the equation would be consistent, the two sides would be consistent if you assume that actually the flow of energy is at the speed given by the magnitude of VR. So what we conclude from this relationship is the following, that energy is flowing at the speed equal to magnitude of VR. So not only in general, the wave and the energy are moving in different directions, they are also moving with different speeds. VR is magnitude of wave velocity divided by cosine. Okay, so this is a very important relationship, which again is coming just from the properties of the anisotropic medium. Now I want to discuss two things, because in this discussion, if you're not very careful about what you're talking about, things can be very confusing. Here we discuss two things, wave propagation versus ray propagation, meaning obviously the two are very different. So what we mean in the wave propagation is the following. You have wave fronts, they are moving at the speed of the phase velocity in the direction k. That's what you call as a wave propagation. So this is the magnitude of the phase velocity. Ray propagation is the way in which the energy moves or energy propagates or flows. So rays, what you're calling ray, so one is wave, other is ray. Okay? Ray moves along the direction of the pointing vector at the speed given by the ray velocity VR. You must keep in mind at what time when you discuss propagation, whether it's a wave propagation or ray propagation, the two are different. If the medium is isotropic, then there's no distinction. But if the medium is anisotropic, there is a distinction which you have to keep in mind so that there's no confusion. And here alpha is angle between E and D. Okay? Now, what is the significance? One is conceptual, because when you're discussing theory, you have to keep these two things separate. These two things also have very important practical implications. When you observe light, let's say through camera, through human eye, through telescope, through microscope, any instrument which you use to observe light, all you observe is the light intensity. You observe how much energy is falling with what is the frequency of that energy per unit area, per unit time. Okay. That is the intensity of light. Okay. So our instruments which observe light, all those instruments, they are responding to ray. Got it? That's very important. Okay. So if, for instance, you would have seen some YouTube, you see some, laser light flowing through crystal. That path is the path of the ray. That need not be the path of the wavefronts. Okay, so let's keep in mind. But it doesn't mean that, or wave propagation has no significance, because the interference, that depends on phase. Okay, when you interfere two waves, then what kind of interference pattern you get depends on the phase difference. So even though there is no direct instrument which measures phase, there are physical effects, namely interference effects, which depend upon the phase. So interference effects would depend upon the wave propagation. And also note another thing. Remember when you wrote down the polarization states, like circular polarization state or elliptical polarization state, what you are doing, you're writing that as superposition of two different linear polarizations. One polarization, linear polarization in x-axis, other in the y-axis, and you said, okay, there could be some phase difference between the two. So the circular polarization is then can be seen as interference of two linear polarizations. So polarization effects, the state of polarization then will also depend on the wave propagation. Okay, if you have more than one wave. So there are different physical situations in which one would observe ray propagation. If you observe the light directly, then you're observing the ray propagation. If on the other hand, you're observing, interference effects or polarization state, then you are dealing with wave propagation. Okay, so this is a distinction we have to keep in mind. All right. Now what we do, so far, discussion has been extremely general. All remember we have used is what? We have used the Maxwell's equations and used the fact that for anisotropic media, D and E need not be parallel to each other. That's all has been used so far. Now what we do, you imagine you have a particular anisotropic medium. That anisotropic medium has principal axis. This word should be principal axis, not planes. Okay, so there is a kind of mistake here. This should be principal axis. Then what we do, you orient your coordinate axis along the principal axis, and we know that permittivity tensor has only 3 components, so we can write down the relationship between D and E. These 3 relationships then between D and E is all we have to worry about. Now what we do, we use these relationships in the equations which were derived earlier from the Maxwell's equations. And we had this equation between D and E from the Maxwell's equation. All right. So what you can do, obviously, you can eliminate D in this equation with the help of, we write every component of D in terms of components of E. Okay, so then there won't be any D vector left, and you will get equations between different components of E. These are the equations you will get. Okay, so equation which comes from the X component, Y component, etc., etc. So these are then the 3 equations for the different X, Y, Z components of the electric field. Notice something very interesting here. K dot E factor is common to all of them. Okay? And then we have, of course, this other factor. Now, I should tell you what is this. This quantity is not a vector quantity. What it is basically you have the K unit vector. This is the X component of K unit vector. So this is a scalar quantity actually. But it's a component of a unit vector. Similarly, this is the Y component of unit vector K and Z component of unit vector. So all these things are basically scalar things. So, but we have these constant factors. Now this has a very important consequence. These 3 expressions for Ex, Ey, Ez. What we can do is, well, first we write on another form. We define, using those elements of the permittivity tensor epsilon x, epsilon y, epsilon z. We define what we call principal velocities. These are just some, you are redefining some constants. Okay, they need not directly have any physical consequence at this point. Okay, so basically the ratio of these things to speed of light. And you can write down the same equation which you wrote earlier now in terms of these principal velocities along the 3 principal axis. And here you have to have the phase velocity. So look at these three components. If you take the ratios of these components, then we have this constant part, of course, which will cancel, and the ratio will then depend on these parts. But these parts, remember, are real. Vx square is a real quantity. This also would be real quantity. Only complex part, remember, was sitting in Ke. But when you take the ratio, that complex parts cancels out. So the ratios of the different components of E, Ex by Ey, Ex by Ez, Ey by Ez, all these three ratios are real. What's the consequence of that? There's no phase difference between the components. Remember the way earlier how we represented the circular polarization? We said, okay, you can have a circular polarization. Let's introduce the phase difference between the two components. And that phase, so if you take the ratio of the two components for circular polarization, there would be a complex part to it. What we have here is a different thing. What you are saying is that when you take the ratio, the ratios are all real. So, which means that there is no phase in that ratio. Just think about this, is very important, okay? Because then the next thing will follow. So if you don't get this, you try to think about this. How, for instance, any complex quantity you can write as a magnitude as a phase factor. So if you have a complex number Z, you can write down equal to rho times Ei phi. Okay, rho is a real quantity. Ei phi is of course a complex quantity. If you have two complex numbers, okay, whose ratio happens to be real, it means they have to have the same phase. There would not be any phase difference between these two numbers. Same thing is happening here. Okay, you have two components. Take the ratio. There is no phase difference between these ratios. But these ratios are real. It means there is no phase difference between the components. If you have the situation that there is no phase difference between the components, what is the state of polarization? That is linearly polarized light or plane polarized light. This is a very, very important result. Okay? Remember, we started with any possible polarization state, but when you put the equations into the Maxwell's equations for an anisotropic medium, what you get is that no, only wave which can exist in an anisotropic medium has to be a linearly polarized wave. This is very important. Keep in mind. Okay, this is a very, very, very important result. And this is so only wave, you can have only linear polarization waves inside the anisotropic medium. It is a set of arguments. If there's any doubt, we can discuss them later in question answer session. Okay. Let's proceed further. Remember, we have those three equations, Ex, Ey, Ez. What we can do is we can manipulate those equations, okay, and add them up. A couple of 4 or 5 algebraic steps. That then leads to what is called a Fractional form. In that Fractional formula, what you do, you manipulate those three equations in such a way and add them up such that the electric field dependence then goes out. And you are left with only an equation which involves the phase velocity, the components of the propagation direction along principal axes. Principal axes are x, y, z axis in our case. That's how you oriented the coordinates. And then Vx, Vy, Vz. Remember how the Vx, Vy came? They basically came from the permittivity tensor along the principal axis. So if you have a given crystal, Vx, Vy, Vz will have some very definite constant value. And if you take a propagation direction, then naturally Kx, Ky, Kz also would have a definite value. Then this equation is a quadratic equation in Vp square. How is it quadratic? For instance, now it's written in fractions, but you can take, you can add these fractions. So denominator would be Vp square minus Vx square into Vp square minus Vy square into Vp square by Vz square. That will be denominator. All these three denominators multiply. What will be in the numerator? You will have Kx square multiplied by this and this. There will be a term which will be square of Vp square. Similarly, if you take this, there will be a term, you will be multiplying ky square with this and this. The denominator you can then take on the other side. So we'll get a quadratic equation in Vp square. This should have been Vp square instead of V. Okay. And what that tells you, if it's a quadratic equation, you can have at most two different values for Vp. You might have same value, and you may not have a real value. That's also possible for a quadratic equation. The solution did not be real. But at most, you can have only two real solutions. So that tells you that for any given direction of propagation in a crystal, what do you mean by direction of propagation? Kx, Ky, Kz get fixed. In a given crystal, Vx, Vi, Vz get fixed. Then you can have only two different values for phase velocity. So we get to this very, very important statement. It looks very simple, but if you read it, it contains the crux of the propagation of light in anisotropic medium. So this quotation I have taken from Born and Wolf. The structure of anisotropic medium permits two different monochromatic plane waves with two different linear polarizations and two different velocities to propagate in any given direction. So they can be two different linear polarizations. Why you are saying that? Because linear polarization will be given by the ratios of Ex, Ey, Ex, Ez, etc. And those ratios, they depend on Vp. Vp itself can take two values, so you can have two different values for those ratios. That's why there are two different polarizations. Okay. And these are linear polarizations. And there will be two different velocities of wave propagation. So this statement of Born and Wolf is very, very important because this contains the crux of the propagation of EN waves in an anisotropic medium. All right. Now let's proceed. Now we go. So that was, what we have to discuss about a general anisotropic medium. Now we talk about a particular class of anisotropic medium, namely uniaxial crystals. And in uniaxial crystals, they are defined by the condition that two, permittivity values along two principal axes are same, and third one is different. Okay? And the third one, in this case, which you are taking in the z direction, that we are seeing is called the optic axis. So in a uniaxial crystal, now the permittivity value in the one principal axis in which it is different, that we take as a z-axis, and that's also called the optic axis. Okay. Now what happens? Remember, we have defined these principal velocities in terms of Ex, epsilon x and epsilon y. Now epsilon x and epsilon y are same, so we get one which is called ordinary phase velocity. Okay, so this is the ordinary from two permittivity values which are same. Okay. Other is extraordinary phase velocity, E. This is O, this is not zero. So O for ordinary. So, and V is then the VZ. These are the basic definitions. Now what we do is the following. We have picked the optic axis, z-axis along the optic axis. Okay. That is fixed because we're dealing with a particular coordinate system which is already aligned with the principal axis. Now, when you go to the x and y axis, we notice the following, that this uniaxial crystal, the x and y properties are symmetric. That means that we can put our x and y coordinates in any way you like. Only constraint obviously is that they have to be perpendicular to the optic axis because z is already along the optic axis. In particular, what we do is we pick the x-axis in such a way so that it's inside the plane containing Z and K. Okay, so Z and K. So X then, if you take, this is the plane of the stream which has the optic axis and the direction of propagation. Then we demand, okay, then we set our x-axis such that that is also in the same plane. Then y-axis obviously will be coming out, because so y-axis is coming out. So this is our setting. So K is then contained in the plane containing x and z-axis, or we can say x is contained in the plane containing z and vector K. So keep this diagram in mind. Now, if this is the angle between Z and K is some theta, then what are these things? Remember, these were the components of propagation vector along x-axis, y-axis, z-axis. So component, and K, this is a unit vector, component of the unit vector. So component of this K unit vector along Z would be cosine theta. This angle is theta. I have not written down here, but this angle between K and Z is theta. Okay, so that is K of Z is cosine theta, K of X is sine theta, and since K is perpendicular to Y, or rather Y is perpendicular to K, there is no component of K along Y. So Ky is 0. That tremendously helps our situation, because remember the earlier equations which we did for Ex, Ey, Ez, that had Kx, Ky, Kz. Now when you put these values of K in those equations, we get these three equations. Basically, these are the equations for Ex, Ey, Ez we had earlier. We had just written down the expressions for Kx, Ky, and Kz for uniaxial crystal. So what we notice in uniaxial crystal, we have two equations which involve Ex and Ez. It doesn't have any Ey. And the third equation has only Ey and no Ex and Ez. Okay, all right. Now, in principle, if you have, three linear equations which are coupled in three variables, then there are certain conditions. The non-trivial solution requires that, determinant of the coefficient should be equal to 0. That gives you some constraint. And then in principle, if you have these coefficients, you can solve it for, Ex, Ey, Ez. But here things are slightly different, because you do not have one unique solution for Ex, Ey, Ez. What we can do is look at, because you have two different separate sets of the equations. And when you try to solve these two equations, what we get are two different sets of solutions. And one solution is called the ordinary wave solution. I will list the solution, then I'll go back to the equation and show you how you get it. In the ordinary wave solution, you say Ey is not 0. Okay? And Ey is not 0, then you go to the equation which has Ey. Then immediately, if Ey is not 0, V0 is Vp. Or rather, Vp is equal to V0. And furthermore, if you put Vp is equal to V0 in these equations, you would get both Ex and Ez as 0. So there is a definite solution which has Ey not 0, Ex and Ez are 0, and Vp is equal to Vo. That is one non-trivial solution to these equations. Very simple. Okay. So this solution we call as the ordinary wave solution. So these are, certain consequences. So what we say, Vp is some V0. In particular, the phase velocity does not depend on the direction of propagation. At this moment, it might seem, by you saying it, but later you'll see it's important, because for the other solution, that's not the case. The phase velocity depends on the direction of propagation. But nevertheless, in this case, it's the case that Vp is equal to V0, and independent of propagation. We also have Ex equal to Ey equal to 0. So the polarization, remember polarization is given by the direction of E. In this solution, only Ey is not 0. And what was Ey? If you go back to the diagram, which we showed in earlier slide, this diagram, okay, Ey is coming out. And it's coming out perpendicular to this plane. And this plane is called the principal plane. remember, the definition of principal plane is the one which contains the optic axis, in this case the z-axis, and the direction of propagation. So our conclusion is that when you take the ordinary wave solution, in the ordinary wave solution, you have electric field only along y-axis, and y direction is perpendicular to the principal plane. So polarization is perpendicular to the principal plane. This is very important. Keep this fact in mind. And now, since only one of them, only one component of E is there, namely Y component. Okay, it doesn't have EZ and EX. So you also don't have Y and Z component of B. So what you have is that vector D, which actually has only Y component, as is E, which also has Y component. The two are parallel to each other now, because they're multiplied with a scalar quantity, not a tensor quantity. So D and E are parallel. D and E are parallel. This is clear. Now let's go back to our diagram which you had drawn earlier. If D and E are parallel, then what happens? Let's go to the directional diagram quickly. This is taking some time. Yes, this one. Okay. So D and E. So what you're saying is D is and E are parallel. Alpha is 0. But alpha is also angle between S and K. This is K, this is S. So if D and E are parallel, so would be S and K. What's the physical meaning of that? The energy flow and the wave propagation are in the same direction. That's the meaning of this. So in the ordinary wave, you have polarization perpendicular to the principal plane, and the energy flow and the wave propagation flow are in the same direction. So these are certain properties of the ordinary wave solution. Ray propagation and wave propagation are parallel. Now we go to, need to keep tab of time. I have to get my watch. I kept it somewhere. I don't know, it's nowhere near. Anyway, doesn't matter. So let's then discuss the second solution. Well, that second solution we call the extraordinary wave. As I mentioned, it's not at all a very creative name, but let's something which has been used, so you have to stick with it. Now, in that solution, we take EY is 0. That is a solution to one of the equations. But that means if EY is 0, then the polarization is in the principal plane. Because Y is perpendicular to the principal plane. We are saying there's no electric field in that direction. So whatever electric field is then there has to be in the principal plane. Remember, principal plane is defined by optic axis, namely z-axis, and the wave vector, direction of propagation. Then what you do is you have two equations. Okay, let me go to the two equations. These two equations. So EY 0, this equation goes away. Okay. You have these two equations involving EX and EZ. Okay. Now the non-trivial requirement for non-trivial solution is that coefficients, the determinant of the coefficients have to be 0. So this multiplied by this minus this by this has to be 0. Okay. So you'll get an algebraic equation, and that will involve VP, VO, and VE. Okay. All right. So that equation then is about the phase velocity. And it turns out we can put that in a very compact form. Vp now is given by this equation. Look at this equation carefully. Okay? Vo and V are given by the crystal because they depend on epsilon x and epsilon z. Those are fixed. This is cosine square theta and sine square theta. And what is theta? Theta is the angle between the direction of wave propagation and the optic axis. So in different directions of propagation, the phase velocity is different. Okay? This is something, of course, you don't expect at all in the isotropic medium. So the phase velocity is a function of the direction of propagation. And this is a particular dependence. Now, what would be, how would you get the polarization? How will you get the direction of E? All we have shown so far is that the vector E is somewhere in the plane, is somewhere in the principal plane, the plane defined by the optic axis and vector K. But where it is, what you can do is, we have the two equations which have, Ez and Ex. Take the ratio. You can solve those two equations and take the ratio. And when you take that ratio, what you get is the direction of tangent of the direction of that vector E with respect to X or Z axis, depending upon how you define that angle. So ultimately, what will happen after a slightly complicated calculation, you will get the angle between vector E and D. And that angle turns out to be this. Well, there should have been a bracket. The bracket should be here. Okay. So it is tan inverse of n0 square ne square tangent theta. So this is the bracket here. In case you're taking notes, please make this a bracket. And then you subtract theta. This is the angle between E and T. Once you got this, you solve the problem of propagation of EM wave in a uniaxial crystal completely. You already know many things. There are two polarization directions, one in the plane of the principal plane, one in perpendicular to the principal plane. And you also know they are in polarization directions now. If you know alpha, in which direction the energy is flowing, for instance, because the angle between K and energy flow is the same as the angle between E and D. This is a very important result. What happened? I think I might have. Okay, so this is a diagram where we have put up all these vectors. This builds upon our earlier diagram. This is the optic axis. Okay, the Z axis. Okay. Wave vector is at some angle theta with respect to optic axis. So whatever the wave vector is, there will be some corresponding theta. Okay. D is perpendicular to K, as we discussed earlier. Okay. E and D make angle alpha, and the same angle is between S and K. Okay. And the expression which you wrote earlier is the expression for angle alpha. And let's go back on what factors does that angle depend. Alpha depends on theta and constants of the crystal, namely, VO and VE. So if you know in a particular direction your propagation, you can figure out what is the angle between S and K. Now, there are two kinds of crystals, positive crystal and negative crystal. Okay. For the positive crystal, the refractive index, basically C divided by VE, is the refractive index NE. That is greater than NO. Or reverse would be VE is less than VO. Those crystals are called positive crystals. And for positive crystals, alpha is greater than 0. Okay, so this angle alpha, if you go back to the equation which you wrote earlier, where alpha and tan inverse, tan of tan inverse, n0 square minus n square times tangent theta, etc. If you go look at that equation, and no is less than ne, you'll get positive alpha. Positive alpha means this. So then S is further away from the optic axis as compared to K, or K is closer to optic axis. This is the case for positive crystals. What do you mean? Optic axis is a physical direction in the crystal. There's a direction of propagation K, depending upon whichever way the wave is going. What you're saying for positive crystals, the energy transmission is further away from optic axis than K. For negative crystals, reverse happens, Ne is less than NO, and there alpha is negative, and S would be closer to optic axis than K. These results, I reiterate, they derive from this formula. So we have these two two important statements about the positive and negative discourse. Dr. Punita, what's the time? I don't have my
Yes,
watch.
just wonderful telepathy. I was just about to ask you,
Yeah.
could we just wait for 2 minutes? We just want to give attendance
Okay.
link to the students.
Okay.
And Dr. Sanjay, we have amongst us Professor Ghatak today evening,
Oh, okay.
and he's one of the panelists.
Obviously.
Welcome, sir.
Welcome, Dr. Ghatak.
He's gone off for a minute or so. Well, it doesn't matter.
Okay.
It's already 6 o'clock, and so if you would kindly, there are not many questions today, only 2 in number or
Yes,
so, and
I will look at the
I request
questions.
the attendance form. Just the announcement, students. There is now the attendance link after the first hour. Please fill the attendance form quickly. If you miss my announcement, and if you cannot see the link in your chat box, scroll up. Please, please scroll up. Please scroll up. So the attendance link is now on the chat box. Please enable the chat box. Yeah, the chat box is enabled. Students, are you able to see the attendance link? Okay, so one is written yes. That's all. Thank you, thank you, thank you very much. Please fill your attendance. Take a break of 2 minutes and then we continue. Vaishnav, please scroll up. Please scroll up your chat box. Move the scroll bar, which is dark gray in color, appearing on the right hand side of chat box. Please scroll that gray bar up, and then you will be able to see the the attendance link. It's being posted again and again.
Okay, so there are three questions. Vaishnav is asking what was repeated the last one. It's one of very early question at 5:08, so I don't remember what I was discussing at that point. The next question is from Charmi Mehta. Why phase velocity is greater than speed of light? Well, I don't think we mentioned and we got anywhere where phase velocity was greater or less than the speed of light. We're not doing anything like that there. What is very interesting is that the speed at which energy is getting transmitted, that was Vp divided by cosine alpha. And since cosine alpha will be less than 1, so the ray velocity would be greater than the wave propagation velocity. That's an interesting result. But we are not seeing anything particular about the speed of light otherwise here. So that I think we'll leave out. Okay, other question by Hardeep is, about this double refraction crystal, how the rays get divided into two polarized rays. Sir, I want to know what exactly happening. So this, in fact, is what we're going to discuss now. Okay, how in uniaxial crystals wave propagates so that you get two different polarization directions. That will be discussed now. Okay, and the other question is, okay, Gitanshi is asking if the wave propagation and ray propagation are different, and suppose the waves interfere, can we see it? No, it's the same wave phenomena. Okay, in the same wave phenomena, two things are happening simultaneously. We'll show some diagrams, will become clearer. Okay, what we can do is the interference of two different waves. So every wave propagating would have a corresponding ray also. Okay? Now imagine two waves interfering. That interference effect between two waves would depend upon the phase difference between the two, and the wave propagation in that sense becomes important. So interference is between two different waves, and every wave would have its corresponding ray also. And ray and the wave would not be traveling in the same direction. That's what we have been saying. Is there any structural difference between positive and negative crystals? Yes, I mean, O is greater than Ne or vice versa. It is arising because of very specific structural differences in the crystals. Now, of course, the derivation of a refractive index from basic theory would be a very, very complicated subject, but naturally these things can be easily measured. Okay, but how they arise to be different is a very different question, and I presume it's a very difficult question to solve theoretically. So positive and negative crystals, yes, there will be some differences. The question is, if you take Ex is equal to Ey is equal to 0, then how can you take D is equal to epsilon ye? See, what you're doing here is that you look at the expression for D. You have three different values which give you the components of D. You have dx is equal to epsilon x Ex, dz equal to epsilon z Ez. If Ez and Ex are 0, so would be dx and dz. So D would also have only y component. Okay, so you have two vectors, they have only y component, and proportionality between them is given by the epsilon y. So this is how I think that can be resolved. This was a question from Surendra Kumar. And there's a question by Justin. Well, what about the group velocity? We're not talking at all about the group velocity, because group velocity would arise if you suppose a number of waves with slightly different frequencies. We have taken a monochromatic wave, so which has only one single frequency. Okay. Obviously, one can then build up a wave packet or group velocity kind of phenomena by adding up waves over a range of frequency, but that's another will be a complicated phenomena. We're not touching that here. That will be very difficult to actually handle. Well, the idea of group velocity, I got, this is Justin was asking, I hope I made it clear. Group velocity arises superposition of waves with slightly different frequencies. Okay, we are dealing only with monochromatic waves, but how group velocity arises, I guess I cleared by that. What energy is required to polarize a crystal in addition to the energy in the electric field, which is this. Okay. Well, whatever energy is used in polarizing the crystal is ultimately coming from the electric field. Okay, and some energy will be consumed in polarizing the material. And if you assume that just the source of the electric field, then we'll have to do that extra work. And particularly if for instance, an electric field is a wave is traveling, a lot of energy losses take place. Okay, there could be scattering. That also will have to come from the source, or there will be a drop in the amplitude of the wave. So yes, whatever the energy is coming from the electric field, unless of course you have some external source which pumps in. So in reality, if you want to maintain the same amplitude, you have to supply the energy from outside. And by the way, talking about technical things, all of you would have heard, if you lay fiber optics, then after a finite distance, or maybe a few kilometers, they are what are called, I think they're called repeaters or something. Those repeaters, because when an EM wave travels in a dielectric, it loses energy. Then after a few kilometers, its amplitude drops. So you have to then supply the energy to the EM wave, otherwise the signal will become too weak. Okay? So we have to supply energy to the EM waves when they travel in a medium. There's a question about, if the ray, between the ray and the wave velocity is different, then what does it mean that the photon energy will reach before the photon reaches? No, that's not happening. Okay. Photon is a quantum mechanical concept. We are dealing with the classical physics. And remember that what we are saying is that the energy and the phase or the wavefronts, we are distinguishing between the two. Okay? Energy is directly physical, something which you can measure by instrument. Phase is something you can't measure. What you can measure is the effect of phase differences if you superpose two waves, because that creates a very specific interference effect depending upon the phase difference. So I won't say that energy is traveling faster than anything else. From where actually the ray velocity propagation arises. I mean, what forced us to introduce ray or ray propagation? Okay. See, what is happening is in the anisotropic medium. How do you handle this question? From where does it arise? Okay. One way to look at it is that it's a very physical consequence of the property of the anisotropic medium. Anisotropic media, all we put in is that E and D are not parallel. That's all. Okay? And then the result which you got about propagation of S being different direction than wave propagation, etc., they all are coming from the Maxwell's equations and the fact that D and E are not parallel. Now, see, in one way, what we can understand the kind of very qualitative picture, okay? In an anisotropic media, when you have a wave traveling, you have the charges in the isotropic media, anisotropic media also oscillating. These charges themselves are producing electric field which are oscillating with the frequency of the exciting field. What our displacement vector D does is lumps together the fields coming from there also. It simplifies in some sense. Okay. So what we then say about the wave traveling in the medium is the following. You think of the external wave which comes and impinges on the sample as an exciting signal. Okay. Exciting signal excites the crystal structure, okay? But the kind of excitation which can exist and sustain in the crystal structure, that depends on the properties of the crystal structure. All right. So these ray velocity being different from the phase velocity, and energy transmission being different from the phase transmission, etc., etc. All these are effects of how then the sustained oscillations take place in the crystal. So that's how I can. That's the only way I guess I can explain the fact that ray velocity and phase velocities are different. Okay, because ray velocity and phase velocity are the combined effect of large number of oscillations taking place in crystals. Oh, yes. The polarization, Priyanka has asked, can you explain polarization without wave nature and with only particle nature of light? Yes, I told you that, how, for instance, the left circularly polarized photons and the right circularly polarized photons, they arise as eigenstates of the quantum field theory. Yes, so you would be able to associate, with appropriate, eigenstates, different polarization states, with appropriate states, not necessarily eigenstates. With appropriate states, you'll be able to associate different polarization properties to light. It's possible. Okay, so this polarization then carries over into quantum physics also. Okay, there are a couple of more. There are 3-4 more questions. So I guess we can deal with them later. Let's proceed now with the lecture, and the remaining question we will try to deal with towards the end of the lecture. Okay, so we're discussing positive and negative crystals have been taken care of. Okay. Okay, now we look at propagation of a wave in calcite crystal. So now we are dealing with certain concrete examples, and some of the questions which are raised about double refraction, etc. They will partially, not fully, but partially get addressed in what we're going to discuss now. So calcite is a very commonly available crystal, which is anisotropic, and it's a uniaxial crystal, and it happens to be a negative crystal. So Ne is less than No, and this is, I have taken a diagram from Hecht. We won't go into the details of the, how this diagram comes about, but this is a part of the crystal, the plane. And what you're doing is, this is one face. You can imagine the face of the crystal coming out of the screen. Okay. And so imagine a three-dimensional thing, let's say in this shape. The optic axis is given this way. In fact, what you have is what's called the principal section. Let's not go. It's a kind of plane inside the crystal, it's a calcite crystal. Okay, and so plane is parallelogram. It's a parallelogram figure, and there are two obtuse angles. And if you join the two, that is the direction of the optic axis in the crystal. Okay, and would you just deal with this? I'll call back later. Okay. So we have this situation, optic axis, given like this. Okay. There's a face of the crystal which is coming out, okay. And we have this wave impinging normally on the crystal. So this incidence is normal incidence. Okay. So angle of incidence is 0. Okay. And this wave, we are shown to be having both the polarizations. There's one polarization in the plane of the screen, okay, and the one which is perpendicular to that. So this can, for instance, can be a randomly polarized light, okay, because a randomly polarized light will have both the polarizations, but with randomly different phases and amplitudes, okay. Or it could be circularly polarized. Doesn't really matter. We don't worry about what. But the important point is that we have both the polarizations in the plane and perpendicular to the plane. Okay? And then this is what is happening. Okay? And what you see here are, remember, notice carefully, it's E ray and O ray. We're talking about the ray propagation in this diagram, not wave propagation. That will come in a separate diagram. So let's try to analyze, understand why what happens. What's the reason for that? First of all, it's a normal incidence. And as far as the wave propagation is concerned, remember, wave propagation is a propagation of wave fronts. Okay? One can show, and there's a half a page derivation, it's given in Born and Wolf, that for wave propagation, Snell's law actually holds. Okay? There's a very wrong understanding that Snell's law does not hold for extraordinary wave. No, that's not the case. When you're talking about wave, for both the ordinary wave and extraordinary wave, Snell's law holds. Okay? Which means, as far as the wave is concerned, okay, let me go back a little bit. So we have this wave traveling in this way. When it gets into the crystal, remember there will be two waves, O wave and E wave. Remember, we have proven that a uniaxial crystal, a wave can propagate in two possible modes, O wave and E wave, okay? Which modes have very definite properties, okay? Namely, about the polarization and the speed. Okay? So we have O wave and E wave instances. But what we already know from otherwise is that the Snell's law valid for both O wave and E wave. So as far as the wave fronts of O and E wave are concerned, they are both traveling, because the Snell's law will be followed. This will go straight through. Okay? Angle of incidence is 0, so angle of reflection is also 0. This will go, the two waves simply go through here. Okay. Now to see what's happening here, I will take you to another diagram. This is again a diagram from Hecht. Here, we are showing O wave and E wave. The earlier diagram had rays. These waves, they show how the wave fronts are traveling. Now, this is a geometric picture. It's not exactly true. So what it's trying to tell you, if you, for instance, take the Huygens principle, you can construct the wavefronts of Huygens principles by talking about spheres, spherical. Okay. So for the O wave, at different points in the, at the crystal surface, you can imagine the spherical wavelets, and wherever these wavelets at the same point, that's a wavefront. So for the O wave, this is the wavefront. Okay. And you can see that incident wavefront is coming this way. The wavefront for O wave inside the crystal is also going this way. There's no change in the direction of travel of wavefront. Now, for the E wave, you don't have spheres, we have these kind of, parts of half ellipses. And one can show that the direction of S is along the axis of these ellipses. We don't have to do this for this diagram. What we need to do is that where in this ellipse you have the same phase, because the point of the same phase gives you the wavefront. Notice that the wavefront is this again. Okay, all right. This wavefront is also traveling in this way. So the wavefronts of the O wave or the E wave, they travel actually parallel. What happens obviously is S is different. And this is happening because we have the normal incidence. All right, so this is something you have to keep in mind. Okay, so going back to the diagram. So what we had is Snell's law is valid for both O and E wave. In fact, the O wave and E wave wavefronts are traveling along the incident direction. They just go through like this. But look at the optic axis. This is the optic axis. Okay. And what we know about the negative crystals, E ray would be towards the optic axis. How do you get that? Because E ray is traveling in the direction of the pointing vector. For the O wave, the pointing vector is the same as the K. K for the E ray is also the same as for the O wave, the previous diagram which I showed. But for the E ray, the pointing vector is at an angle to K. Okay. That angle we had defined as alpha. Let's go back what that angle was. This angle. Okay. All right. For E ray, there would be an angle between the pointing vector and K. Not for O wave. Because for O wave, D and E are parallel anyway. So S and K are also parallel. D and E are not parallel for E wave. And that angle, of course, we had an expression earlier, the tangent function, this one. So you can put, for instance, if you want to use this formula, you have to use theta. And what is this theta? This theta is the angle between optic axis and the K. So if you go back to this diagram, K is in this direction, optic axis is this. And from geometry, actually, one can work out what will be the angle between K and optic axis. That angle is theta. Okay. So you put that angle in that expression, you will get the value of alpha. Since it's a negative crystal, the alpha would turn out to be negative, which tells you that S would be closer to optic axis than the K. So that's what you're saying, because S and E ray are traveling in the same direction. Remember, when you say E ray, that's the direction in which the energy is flowing. That's the direction of pointing vector. and S is now closer to optic axis. So optic axis is like this. And you can see that optic axis, the angle between axis and K is less for E ray than for O ray. And this E ray is polarized. So we have, these two different rays shown here. O ray is perpendicular to the principal plane. Principal plane, remember, is defined by optic axis and K vector. Okay? And K vector is here, optic axis is there, and the polarization of O ray is perpendicular to that. This we have shown. Now EY is non-zero. So that is the polarization of O ray, and the of the E ray is in the principal plane. That is shown like this. And vector E is perpendicular to S, and that's why we have shown them as oscillating perpendicular to the direction of S here. So this is what is happening. You have an incident wave with all kinds of polarization states, doesn't matter. Inside the crystal, it gets split up. The rays get split up into twos, okay? An E ray and an O ray. And these rays travel in different directions and they have different polarization. And that's the case with both the wave also. Okay, though we have shown the rays, traveling as separate. But remember, the wave fronts are traveling in this way. So what is happening is, if, for instance, this is a very thin ray, thin beam of light, so like a laser beam, then you will actually see it being split into two. Because when you see some light, all you're doing is you're recording the path of the ray, the path of the energy flow. So you will see two different rays, and then you will see these two different rays coming out parallel to each. They'll be displaced relative to each other. What is important, that these two rays have orthogonal polarization. Both of them are linearly polarized. One is perpendicular to the principal plane, other is parallel to the principal plane, in the principal plane. So they are orthogonal, but they are linearly polarized. So this is how a calcite crystal, if you take a narrow beam of light, will be able to separate it out into two different two rays with the different plane polarized, orthogonal plane polarizations. Okay, so this is kind of double refraction. Okay, you have two refraction, but this is coming from a very simple case of the incident light being normal to the plane of the crystal surface. Okay, now, okay, I think that's all. I already discussed the polarization. This diagram has also been discussed. So these are propagation of O and E waves. Now we just discuss two simple instruments to further apply these ideas. This is an old, this more of historical interest, a Nicol prism. Okay. A Nicol prism was used in 19th century, early 20th century to produce a polarized beam of light. And how does it work? You take two prisms of calcite, this one and this one, and they are ground so that this angle is 68 degrees, and there's a reason why it's done, but let's not go into those details. What you've done, you're joining these two prisms with a material with a very particular specific refractive index. And that specific index is such that which lies practically between NO and NE for calcite. Okay? It's some material called Canada balsam that's used to join these, fuse these two prisms together. And the importance of Canada, that material, is that its refractive index lies almost between NO and NE. Remember, for calcite crystal, it's a negative, so NE is less than NO. There's a gap between the two, and Canada balsam lies practically between the two. Okay. Now, what happens here? Remember, this is not non-normal incidence, so of course the two rays get deflected. There will be different angle of refraction depending upon the phase velocities, and the phase velocity of the two, since it's we have different theta, there would be another two rays will get diffracted by a different amount, okay, because the phase velocity of O wave and E wave are different in general. So we have these two being separated out. What happens is that for O ray, there is a total internal reflection. Because for O ray, remember, is the refractive index of refractive index for O. Okay? And the Canada balsam has the refractive index less than O. Okay? So there will be a total internal reflection. The refractive index of O ray in the Nicole prism is more than that in the Canada balsam. So there would be a possibility, depending upon whether the angle of incidence is correct or not, there would be total internal reflection. So O ray gets totally internally refracted at this boundary and comes out this way. On the other hand, the E ray, that is able to go through. E ray doesn't suffer any total internal reflection because the Canada balsam refractive index is more than that for the refractive index of E in calcite. So that ray goes through, okay, and then it comes out here. So what then you have here is a wave which is polarized. It's a plane polarized, it's a linearly polarized wave, which is angle, and the polarization direction is in the principal plane of the crystal. Okay, so that's how you are able to create a polarized light with the help of Nicole prism. This was one of the simplest instruments to produce polarized light. Other set of devices which are very useful, like quarter wave plate, half wave plate. They are a class of devices which are called retarders, meaning these devices, they produce phase difference between different waves. Okay. Now, let's see. Okay, so what we do for this is a diagram, again taken from PACT. So what you have done here is you have cut the crystal surface differently than the earlier case. Earlier case, optic axis was coming at an angle to the crystal surface. Here, the crystal surface is cut parallel to the optic axis. Okay, and this is the angle of incidence. So this is the angle of K, direction of K. So the angle theta between optic axis and vector K is 90 degrees. Okay. Now you can go back to the equations. Remember, there were two equations. One was Vp square cosine square theta plus Vo square sine square theta is equal to 0. Okay. Other was the equation about alpha, okay, which both had theta. So put theta equal to 90 there, 90 degrees. And angle, of course, incidence is normal incidence. What we get from those equations is that the phase velocity of extraordinary E wave, now we're talking about phase velocity, that is equal to the VE. Let me go back to that expression so to tell you how that is arising. I just talked about those. This is the equation I'm talking about. Okay? In this equation, put theta equal to 90 degrees. Okay, so VP will be VE. That's what I meant. For the extraordinary wave. This is one. The second would be this equation. Put theta equal to 90 degrees. Alpha equal to 90, theta equal to 90 degrees. If you put the proper limit, you will get alpha equal to 0. So, in this case, what's happening is we have normal incidence. Okay. E wave is traveling with VE. O wave is traveling with VO, and the two are different. Furthermore, notice that alpha is also 0. So, not only waves are traveling in the same direction, there's no separation between the energy of the two waves. This elliptical wavefront is telling you is a wavefront for E wave. Okay? The spherical wavefront is a wavefront for the O wave. They're both along the same direction. S and K are in the same direction. So basically, now we have both O and E wave traveling together, but these waves are traveling with different speeds. One is traveling with speed VO, other is traveling with speed VE. Okay. NE is less than NO for calcite crystal, so VE would be more than VO. But they're traveling together. And furthermore, both of them have orthogonal phase, orthogonal polarization. One is in the plane which contains a principal axis. So the principal axis, optic axis, and the K. So one, the E wave oscillations would be like this, okay, and O wave oscillations will be coming out of this plane. Okay, so they have two different oscillations, two different polarizations, but traveling at different speeds. So that introduces a phase difference between O wave and E. All right. So when these two waves come out of the crystal, depending upon how much distance they have traveled inside the crystal, there would be a phase difference between the O ray and the E ray. Okay. And that phase difference is basically, you know, it's proportional to the distance traveled in the crystal, okay, and the difference of the two refractive indices, NO and E, because that gives, they give you the VE and VO and VE. So there's a phase difference introduced. So when these two rays come out, they are traveling together, but there's a phase difference. Now remember how you can produce different polarization states. You can produce different polarization states if you take two orthogonal polarization. If you introduce a phase difference between them, you get different polarization state. If the phase difference is pi/2, you get circular polarization, for instance. If some other value, you get elliptical polarization. If the phase difference is a multiple of pi, you get plane polarization. So depending upon this distance d, you can get different polarizations on this side, because the wave on the other side of the crystal would be superposition of two waves with orthogonal polarizations. And the two waves with orthogonal polarization would have a phase difference. So let's go back. Let's see what's happening here. Here you're putting some, all you require is light with some, it could be unpolarized light, for instance. That unpolarized light will induce an E wave and an O wave in the calcite crystal. And given the arrangement here, so that optic axis is parallel to the face, okay, and K is then perpendicular to the optic axis, O wave and E wave are traveling together, but they are traveling at different speeds. So there is a phase difference introduced between the two. Okay, so when they come out, then the two interfere, and now you have two orthogonal waves with different phase difference. You get a state with a definite polarization. Okay, so that's how the retarders they can produce phase difference at different polarization states. For instance, if this, you know, the phase difference is pi/2, so then an unpolarized light here will come out as a circularly polarized light. Okay. And pi/2 phase difference. Okay, let me just say pi/2 phase difference. So that's called the quarter wave plate. Okay. Half wave plate will produce a phase difference of pi. There's a use of that also. You just change one, you get a plane wave in a particular direction, but let's leave that out. So the point is that these retarders, then they can be used to produce waves of different polarization. And further, remember, this incident wave doesn't have to be unpolarized. You can introduce a linearly polarized or a circularly polarized wave here. Retarder will change the polarization character of the wave. It can convert a plane wave to a circular wave. It can convert a circular wave to a plane polarized wave. It can do something with the elliptical wave also. Okay. So depending upon the width of these retarders and the refractive index of the material, NO and NE, you can change the polarization character of the wave also. Okay. So these are the two, since we are dealing mainly with the concepts, so we have tried to understand how these two class of devices, one was, Nicole prism is a device which creates a polarized light, and retarders is a general class of devices which also create polarized light, but they can also then modify the polarization character of an incident light. They are two general class of devices which are very useful. So let's stop here as far as the lecture part is concerned, and now we can try to address the questions. We still have around 10-12 minutes. Okay, let's see. Okay, we are discussing can we explain polarization without wave nature and with only particle nature of light? Yes, that question I'd answer. Sir, friction is an EM force, then why don't we mention it in EMT? That's a very, very interesting question. Friction also, I can't really answer that question. I'll have to think about that. I mean, yes, the friction is ultimately arising from electrical forces, and why it is not discussed. I would guess the origin of, we have a qualitative understanding of how friction would arise from, ultimately from electromagnetic forces. But I think qualitative understanding is not straightforward. The actual derivation is not straightforward. So it will be a fairly hard problem to be discussed in an undergraduate EMT course. Okay. Let me just give you a rounded answer. See again, what are positive and negative crystals? I mean, we have discussed that, for positive crystals, NO is, NE is greater than NO for positive crystals, and for negative crystals is the other way around, which basically, have these relations, which of the refractive index is greater, that determines whether crystal is positive or negative. Optically active medium, yes, we have not discussed that. In fact, the theory of optically medium is a very complicated theory. There is, a theory due to Fresnel, I think, which is a kind of very heuristic theory, okay, phenomenological theory, which doesn't go into the details of how optical rotation takes place. Yeah, that will be very complicated, so we are not discussing that. And there's a question of that wave propagation direction and energy propagation direction can be different in anisotropic universe. Shouldn't they be always the same? Okay. See that how we define a wavefront. Okay, though of course in pictures we do show wavefronts at planes and etc. etc. Phase is basically where an oscillation in at which, not I won't say position, but at where is that oscillation, an oscillating phenomena is in its cycle. That is the phase. Okay. And when you call up a wavefront, that is basically, okay, let me just say, I would say this way, a wavefront is an appearance. For instance, suppose you're standing on a beach. You see this wave of, what you call sea wave coming towards you. You try to ask the question, what actually is traveling towards me when you watch a wave, sea wave coming towards you? Is it the water which is traveling towards you? No, because the water molecules practically remain where they are. They go around in circular orbits, okay? And it's what you observe as a wave, what you observe as a wave, suppose you observe a crest of a wave, okay? What you observe is that crest is traveling. but there is no material which is traveling with that crest. So a wavefront is in some sense an appearance. It doesn't mean that the energy energy is something very directly physical. Okay? It doesn't mean that energy also have to be traveling in the same way as the wave crest. Okay? And I would say is that in anisotropic media, in fact, we actually prove that the two can be different. But in a kind of heuristic argument, if you keep in mind that the wavefronts are appearances, they play a role in interference. But if you just observe a wavefront of a single wave, then they're just appearance. And there's no reason for us to then assume that the energy should also be traveling in the same direction, because that wavefront is just an appearance. For energy, you have to think of something else. Some other phenomena you have to take into account. Okay, there's an audio is low. I'm sorry about that. I'll bring my laptop closer microphone so that. Why do we study polarization in different medium? Well, I'm sure that it has many practical applications in many number of devices. Okay. One thing which we should be note down. See, when you think about light, light is a very special class of electromagnetic wave. For instance, most of the natural phenomena which create light, they create randomly polarized light. You require a very, very specially designed instruments like lasers, to create light which is coherent. On the other hand, if you talk about radio waves, then the polarization and the phase of the radio waves can be very well controlled. And a lot of information, for instance, radar radio waves, etc. A lot of information then can also be contained in the polarization. So for light, it appears polarization, since most of the light is randomly polarized, why we're spending too much time on polarization of light. Okay? But polarization for EM waves, since polarization for other EM waves can be created easily, then it can be then I think it will have great applications there. There's a question by Thomas. A practical linear polarizer is always limited by the extinction ratio of the polarizing element. Yes, so when the transmission axis, the linear polarizer is aligned perpendicular to the incident ray, say from a vertically polarized laser source, what will be the SOP of the emitted beam? Will it be the same as that of the source, or will it have some random SOP? Well, I can't. SOP is state of polarization, I guess. Let me read carefully again. It's a long question. Practical linear polarizer is always limited by the extinction ratio of the polarizing element. So when the transmission axis of the LP linear polarizer is aligned perpendicular to the incident ray, say from a vertically polarized laser source, what will be the state of polarization of the emitted beam? Will it be the same as that of the source, or will it have some random SOP? I don't think it will be random, since we are passing it through a polarizer. What you're saying is that the polarizer may not be 100% in some sense. So the extinction along the orthogonal axis will not be, exactly zero. So it would be the ray then which comes out. It will not be polarized only along the axis of the linear polarizer. There could be also traces of other polarizations, particularly close to that. Okay. So how would you characterize a beam which is not made up of one polarization, but other polarization close to that? I won't say that other polarizations would be randomly having phase differences. I think there would be, if it is a linear polarizer and a good linear polarizer, these other polarizations would not have a random, unless the extinction phenomena itself is random. Then these would be randomly polarized, and that would create some problem. So that's a difficult question to imagine what exactly will happen. That's a very interesting question to ponder over. What is the exact nature of the light which comes out of not a 100% polarizer, but a polarizer which does the job maybe let's say 95%. I think that's an interesting question. We need to think about that. Electric polarization itself is a kind of friction. Well, Harsh has answered the earlier question. Yes, in the way that when you have polarization and particularly, no, I need to think about, I don't think that's immediately. The answer, at least what I had in mind, that if you have an oscillating wave, so these charges are oscillating and oscillating charges, they emit radiation, that's the energy loss. But in friction, you are not dealing with the radiation, energy loss due to radiation. Okay, there's some other phenomena playing a role. Okay, somebody is saying it's disconnecting. So sorry about that. Oh, there's a very important observation by Saurav Verma that friction is a non-conservative force, but electric forces are conservative. So how can you get a non-conservative force out of conservative force? Oh, that's another very interesting. First of all, I mean, we do notice, for instance, if you think about, collisions, I'm just talking about the conservative and non-conservative, etc. Okay, if you think about, collision between gas molecules, okay, we know, for instance, gases have viscosity, which is a kind of friction effect. Okay, on the other hand, all the interactions among molecules of a gas, those all those things, they conserve energy, and but nevertheless, when you bring a large number of these molecules together and look at the statistical effects of their motion, then we do see phenomena which can have energy dissipation effects. So the ultimate source for these things, I guess, would lie in the statistical physics of these things. When, for instance, an electron, it just comes and interacts with a single proton or another electron, that collision is elastic, no energy loss. But if you think about, this single electron coming into a large collection of other charged particles, then you think about there is an energy loss. An energy loss in the sense that if it had a directed momentum and energy of a translation energy motion, which is directed, when it enters a medium with large number of other charged particles, that directed energy gets lost. It becomes more randomized. So my guess is that what we should think about friction arising from electromagnetic forces is to have to go through statistical nature of the phenomena involving friction. I think that's the only thing I can say at this moment. Okay, I guess our time is just 3-4 more questions. Oh yes, there's a very interesting question that some species can detect polarization. Yes, there are certain, through natural selection, certain animals have eyes which are sensitive to polarization. In fact, even human eye has some very, very low sensitivity to polarization. And I've been told that there are certain exercises, something can be done, or certain conditions can be created so that human eye becomes more sensitive to polarization. Yes, biologically there are, and you can see why that's happening, okay? You can devise such molecules, such material, which will respond, which will be anisotropic, and which will respond differently to different polarization states. It's possible to do that. Anisotropic media do that. So if your eye was made up of such substances, or it might, if it has certain such substances, yes, your eye can, an animal biologically evolved eye can respond to polarization also. Oh, okay. the question is different. So how they come when there is no polarization? Okay, I should have been qualified. Okay, see, there are most of the natural light when it gets produced, for instance, in sun, for instance, that is unpolarized. But there are other phenomena, again natural, which can create partially polarized light. For instance, polarization by reflection. You look at the reflection of sunlight from water of a pond. The reflected light from a pond is partially polarized. So there are natural phenomena which modify the state of polarization. So there are, one should qualify. One shouldn't say that there are you cannot have polarized light in nature. Though it is true, most of the natural phenomena do create polarized light. Light, I'm saying, I'm not saying about electromagnetic waves. Those are, because electromagnetic waves stand on a wide spectrum. Radio waves, which pass through galaxies, interstellar medium, they can have some polarization properties, which are very useful in astronomy. Okay, so you're not talking about that. You're talking only about the light. So there can be natural phenomena which modify or create which modify the polarization vector. So a completely random polarized light can become partially polarized, passing through some natural phenomena. Reflection is a very common example. Scattering also does the same to some extent. Okay? So yes, we should modify those things. So I guess most of the questions there are certain questions very interesting. I don't know the answer, which one I guess need to think about, particularly the one about friction and how friction can arise from EMT. My guess would be that you have to take the statistical physical nature of the phenomena which actually produce friction into account. Okay. Other thing about what will be the state of polarization of out of a polarizer which is not 100% but which has some extinction, so that the light which comes out is only, let's say, partially polarized, not fully polarized. What will happen to that? How will you decide the state? So these are two very interesting questions which we need to ponder more over. So thank you, all of you, and I hope that whatever we discussed in the past 2 days is useful. And once again, thanks to Dr. Punita and Dr. Bindal and all the students who sat through these lectures and posed some very, very interesting questions.
Hello. Yes, Dr. Sanjay. Thank you so much. An engrossing lecture, a lecture from which you just cannot take off either your ears or your eyes. Definitely. And I become a little sad when I see that I have to look after some organizational things, and hence I miss a sentence or so. So even for all teachers, this was a very engrossing and a very informative lecture. So I thank you once again wholeheartedly. Could you please switch on your video for just a moment? So we would like to keep, we also keep a screenshot of the participants and of the panelists and so present. Yeah. Thank you so much. And from the entire team of mine, although this is not your last lecture, but for today's lecture, thank you so much. And we shall then continue with other subjects along with you as and when you schedule it with us. Thank you so much once again.
And a special thanks to all the people who are participating.
Yes, for sure. They have patiently sat and asked some very relevant questions also. Yes. So, sir, the students are asking for your PPT also.
I will leave the PDF lecture notes. The PDF.
Yeah. Okay. Thank you so much. Thank you so much. Okay, so Dr. Partha Goswami has already joined us for our last lecture of today. I request Dr. Mansi to share the screen with the intro of Dr. Partha Goswami. Hello, good evening, sir.
Good evening. The video is disabled.
Sir, 1 second. We are just give half a second, and Dr. Okay. Mansi, could you please, sir, you can enable it yourself, I think.
No, I can, but the message that is coming is you cannot start your video because the host has disabled it.
So just a second. These
Ah,
paid versions of these webinar conducting platforms, etc., have several have several controls.
problems.
And Dr. Mansi, you can.
Please try it again.
Okay, let me. Ah, I
Yeah.
think now it is
So they
visible.
provide you with n number of possibilities of combinations, and
Okay.
sometimes it just takes a little bit delay. So thank you so much, the host and co-host, Dr. Mansi and Dr. Parul. So, sir, welcome you once again
Yeah,
for another series of
my pleasure.
classical dynamics lectures on Hamilton's equations today.
Yeah.
So I would just introduce you 1 minute all over again, and Dr. Parul, can you please stop the recording and then start the recording again? Meanwhile, please share Dr. Partho's introduction slide.
Yes, ma'am, I'm doing.
So, sir, just a second. So, today you are going to teach us about Hamilton's equations, right?
Just one correction. I have now 32 papers to my credit, not 26.
Okay, okay, okay.
32 papers.
Sir, any number more than five is enough to scare youngsters and enough to inspire teachers. So, and definitely such a large number is an inspirational thing, and the students should see how, along with teaching, teachers indulge themselves in deep research. So, Dr. Partha Goswami, he's an MSc, MPhil and PhD from University of Delhi. He's presently an associate professor in physics in Deshbandhu College, University of Delhi. And he has done his graduation with first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics honors students for the past 30 years. His area of specialization is condensed matter physics theory. And he has about, sir, how many? 30 or more?
32. To be precise,
So 32 research
papers.
papers to his credit, mostly under the sole authorship, published in prestigious journals of physics. And as I said yesterday also, he is a very, very voracious reader, providing us every day a very small but very informative piece regarding pedagogy, how we should teach, education, and so on. So thank you so much, sir. Dr. Mansi, please share the slides of Dr. Partho
Sure.
Goswami for continuing with classical dynamics lectures. So, sir, just it will take a fraction of a minute to share the screen.
Yeah.
So, the students, Dr. Partho has provided us with 2 books or as PDF for this portion of classical dynamics, and that shall be supplied to you, those who are attending today. And also, Mansi, it is not here yet visible, your screen.
And in special theory of relativity also, I have provided 3 books, I believe. You can share with them, share with students those
Yeah,
books.
Mansi, are you able to do it? So, sir, just a minute, we will.
No, it's all right. It's all right.
Yes, Dr. Parul is trying to.
Yeah, it's okay. I mean, if you are not, then I would share the screen. Is it possible? Yeah, very good. Yes, it just takes a minute or so. So please go to the screen slide screen mode, slideshow mode. Yeah, okay. So here, yes. Yes.
So
So I
shall I
request
make a
Dr.
start?
Parul. Yeah, yeah, please. Thank you, sir. Please
Okay.
continue. Please
Okay.
continue.
So we start with a few examples of how to apply the Euler-Lagrange equation to solve various problems of dynamics. The first problem that I have taken, if the first slide, is here one can see we have two masses M and M, and there are three springs of each of spring factor K, and the two on the left and right, they are joined rigid to some kind of rigid support. And if the system is
Sir,
disturbed,
you are at slide number S1A.
S1A, that is
Yeah.
the number one slide.
Okay, so please go back to the initial slide. The first slide, slide 1A. No, this is the next one. The previous one. Yeah, here. Here, this is the first
Yeah.
slide. Exactly.
So the
Exactly.
problem is we have two masses, M and three springs with spring factor K each. And our if we disturb, give a displacement to the system, the oscillation of the system will take place. And my task is to show you using Euler-Lagrange equation. My task is to show that there would be two distinct modes, the two distinct eigenfrequencies, that is to say, and movement of particles will be with same amplitude and same phase, and that is one mode. The other mode will be with same amplitude but opposite phases. So in the solution, I have DOF, degree of freedom, I've chosen to be in this case 2, which I don't need to uh, explain because motion is taking place along, say, x direction. The two coordinates, x1 and x2 of the two masses are good enough for our generalized coordinates. And we can write down kinetic energy as half m x dot x1 dot square plus x2 dot square, and potential energy half k x1 square x2 square, and for the third x1 minus x2 whole square. Lagrangian being L minus L equal kinetic energy minus potential energy. So it becomes what is written out there. As I said, our generalized coordinates are 2, x1 and x2. So we already have talked about the Euler-Lagrange equation in our previous uh, discourse. So using the Euler-Lagrange equation, one gets the two equations which I have shown at the bottom, mx1 double dot plus k times 2x1 minus x2 and mx2 double dot plus k times 2x2 minus x1 equals 0. Now I go to the second slide, which is S1B. Well, I with those two equations which I have obtained just now, I stated, they are added and subtracted. And upon addition and subtraction, we obtain first equation mx1 double dot plus x2 double dot k x1 minus x2 equals 0. And upon subtraction, we obtain the other one mx1 double dot minus x2 double dot plus 3k x1 minus x2 equals 0. Evidently, these equations are equations of harmonic oscillator. So solution will be x1 plus x2 will be something like a1 cos omega t plus theta, x1 minus x2 a2 cos omega some or different omega, which would be square root of 3k by m, and this omega, the earlier one, is square root of k by m, the spring factor divided by the inertia factor. So this is very easy to see. The students are familiar with equations of motion of a harmonic oscillator. So we have solutions for x1, x2, x1 plus x2, x1 minus x2. So these solutions for x1 and x2, the displacements would then be, as I have written down, a1 cos and a2 cos omega t plus theta and all that. So this is, so we see that there are two eigenfrequencies. There are two modes of oscillation, two different frequencies. One, the first angular frequency corresponds to square root of k by n, and the second one is root 3 times the earlier one. And the solutions are as shown. With this, we go to the slide number S1C, where, well, we have the same thing. The note that I have at the bottom, the solutions unveil that two distinct mode exist here. The mode with eigenfrequency omega corresponds to movement of particle with same phase, whereas the mode with eigenfrequency omega dash corresponds to movement with opposite phase. And why same and opposite? The plus and minus sign explains that. Amplitude in both the cases remain the same, and the general solution is just this. So this is our first problem. With the second for the second problem, I go to slide number S2A. Problem of, I am deliberately slide number S2A, which is our fourth slide. Hello? Hello? Hello?
Yes, sir. Yes, sir.
Slide number first, second, and third, S1A, S1B, and S1C have already been discussed and dispensed with.
Okay, sir, you will have to tell the slide number, because
Slide number, I have just said that it is now slide number S2A, S2A, which is in the order fourth slide.
Okay, Dr. Parul, please go to slide number S2A. I think there is a problem with a network connection, sir.
Yes, ma'am.
There is a network connection problem. Please,
Yes,
1
ma'am.
minute.
Okay, so shall I wait for some? I think I should.
Is it just
wait.
2 minutes? It's just network issue.
Yeah, yeah.
Yeah.
No, it's
Yeah.
Yeah.
It's okay.
So is the first problem because there was a mismatch of projection of slide and what I spoke about. Is the problem first clear to everybody? Problem of two masses, three springs. Is it clear?
Please enable chat so that the students are able to write. Please enable chat. Meanwhile, somebody can. Please
Not
enable.
clear.
So, ma'am, we missed 1B and 1C. No, it's not clear. Somebody says no, somebody says yes. So.
Oh, actually, they missed 1B and 1C.
Yeah, so.
One,
Okay.
they have, please go to slide number 1A. Slide number 1A, applying Lagrangian equations, I got at the bottom two equations for the variables x1 and x2. Second order first degree equations. Is the, in the slide S1A, is this clear? S1A, first slide. Please go to plus to explain.
Sir, there is a network issue. Please wait a minute. Sir, please.
Right.
There is a network issue. No, backwards, please. Backwards. Slide 1A. Yeah. So we are now at slide 1A. Sir, actually, you can look at this particular screen itself and speak. Whenever you speak, it will be changed next, and you'll be able to see that it is changed. So it is now slide 1A. And that's the first slide of your device, of your PPT. Yeah, students, we have followed. There was a problem. She was moving, but it was not getting conveyed. Now it is, once again, we are starting off. Sir, can you hear me? Students, I request you to kindly have patience. Give us 2 minutes. It looks like Dr. Partha Goswami has logged out. So he will join in again. Just have a little bit of patience. I will make other announcements during that time. Sir, can you hear me?
Yeah, I can hear you.
There was
But
some network glitch, some network problem.
so,
So,
shall I?
So, sir, slide number 1 is visible, and you can look at your.
Yeah. Slide number 1 is visible. What I want to just remark about slide. After that, I'll go to the next slide. I already have explained the nitty-gritty. I want to with this Lagrange, which is L equal T minus B involving x1, x2 and their derivatives, time derivatives. We get two Lagrangian equations in terms of x1 and x2 and their derivatives, of course. They are second order first degree differential equations. With this, now I go to slide number 2, sorry, 1B. 1B.
Is it okay, sir?
1B. Yeah, it is okay. It is okay. Okay. So the two equations which we have obtained are added and subtracted. Doing that, I get two more equations which I have written down right in the beginning after the problem part. Upon adding and subtracting respectively, we obtain this and this. We have written down. Looking at these two equations, one can easily write down, because they are the differential equations of harmonic oscillator. One can write down the solutions as I have written. X1 plus X2 equal A1 cos omega t, where omega angular frequency is square root of k by a, and minus X2 is A2 cos omega prime t. Omega prime is square root of 3 times square root of k by m. And they in turn adding and subtracting yield the values of x1 and x2. So one notices that there are two modes of same amplitude, modes meaning eigenfrequencies of oscillation. In one you have plus sign, in other you negative sign. One corresponds to same phase oscillation, other corresponds to opposite phase oscillations. Eigenfrequencies are different. Now I go to slide 1C and look at what is written at the bottom. Slide 1C. Slide 1C.
Sir?
Slide,
Sir? Is okay?
Sir, can you please, sir, can you please shut off your video because your voice is not clear at all? Yes, that's, I mean, because of network issues, sir,
yeah,
the bandwidth requirement is large to show our video. So if you just shut off your video, it will run even smoother. Sometimes network is a problem throughout the country and we all understand it thoroughly. Yeah. Okay. Sir, please continue with just shut off your
solution.
Sir, your video is not shut down. You shut your video.
Oh, it is shut. It is shut. I think it is shut.
Now it is shut.
Yeah,
Yes, sir. Yes.
Yeah, it is shut. Solutions unveiling frequency or identifrequency omega forms to the movement of phase and movement identity. And which is slide number 2A. Slide number 2A.
On which slide, sir? Your voice is not clear.
Slide number 2A. 2A. A for umbrella, 2A.
This one?
Yeah,
yes.
Yeah.
Slide number 2A. Actually, sir, are you using a 4G or a network, a Wi-Fi network today?
I am using actually my service provider somehow, I don't know, their thing is not working. So I am using 4G, the Wi-Fi, which is, that is data, mobile data I am using.
Yeah, sir, that's the reason. Because of 4G, the voice breaks. Only with the Wi-Fi, it runs smoothly. Anyhow, doesn't matter. Please continue.
Right. Now, in the problem, we have electromagnetic. The Lagrangian will be, as I have written down, half particles of nothing. Electric field, in fact, is given by the gradient of negative gradient of the scalar potential and together with the antiderivative of vector potential A with time. And vector potential A itself is defined as B, magnetic field B equal curl of A. These definitions are in fact clear to our students because they already have studied basics of electromagnetic field theory. So one sees that if phi goes to scalar potential, phi goes to phi dash equal phi minus some del psi del t, or A goes to A dash equal A plus gradient of psi being an arbitrary function of coordinate and time, then nothing changes, field doesn't change. So these kind of transformations are called gauge transformation. So my task now is to get the Lagrangian L, which is written down half mv square minus q phi plus q times AV. So one can see, looking at this expression, that rather than field, the magnetic field, vector potential is it carries more significance in Lagrangian, and we shall see also in Hamiltonian the vector potential is involved. Say I would calculate shortly Hamiltonian of a charged particle in electromagnetic field, and I will find that that too involves the vector potential. So with this, I go to the slide 2b, which is continuation of the same problem. Slide 2b. Slide 2b.
Sir, is it okay?
Slide 2b. Now, okay. Yeah. The Lorentz force, of course, is known on a charged particle Q E plus V cross B. And E electric field is also known gradient, negative gradient of scalar potential and antiderivative of vector potential with time. And B is curl of vector potential A, B being the magnetic field. So substituting the expressions for E and B in the Lorentz force expression, we get equation 12.36. As I said, these slides have been taken from my book on mathematical physics. So equations are not 1, 2, 3, 4. In fact, this belongs to chapter 12 and equation number 36. Anyway, so we have expression for the Lorentz force, and we have taken the x component of the right hand side. So mind you, gradient of phi is a vector. So x component of gradient of scalar potential phi will be del phi del x, well known. And similarly, vector triple product V cross del cross A, x component of that will be what I have written in equation 12.38, del x of V dot A and dAx dt plus del Ax del T. These are fundamentals, so I will not harp upon them. I will move to now the next slide, that is the sixth one, which has been named as S3. S3. It is a continuation slide. So S3. So yeah, it is okay. Okay, it is okay. So X component of the Lorentz force, in view of what I have put in the earlier slide, comes out to be what is written here as the first equation. Fx equal q times whole multiplied by minus del phi del x minus del x del t plus del x of v dot a minus dx dt plus del ax del t. And this could be written in a very simple form as fx equal del u del x ddt of del u del vx, del u del vx. Sorry, there is a mistake. It should be del u del vx. So here we have introduced the function u, which is q times the potential function. Q phi is scalar function, and q times v dot a. V dot product of v and a will definitely also will be a scalar. So our scalar potential u, effective scalar potential u, becomes q times phi minus a dot v, and Lagrangian being our task was to get the Lagrangian. So Lagrangian of particle being kinetic energy minus potential energy. Particle is assumed to be a single particle, non-interacting. There is nothing in the neighborhood. It is moving in continuum. So kinetic energy is half mv square, and expression for u, which we have obtained in 12.40, substituted, gives me the Lagrangian, which is our 12.41. Please make a mental note of the expression for Lagrangian. I will shortly use it for calculating the Hamiltonian of a charged particle. With this now, I go to S4, S4,
So this one
which
is okay.
is S4. Yeah, this is okay. Perfect. Uh, I have taken an example first. I have a mass at a height h, and suppose the height is taken as the z direction. So Lagrangian of the body will be kinetic energy minus potential energy. Ground level I take to be zero potential energy. Uh, Zero potential energy level, and z direction I take to be the downward direction. So Lagrangian could be written as half mvz square minus mgz, where g is acceleration due to gravity, and that leads us to the through Euler-Lagrange equation, leads us to the result minus mg equal d dt of mvz. And certainly then the solution for vz with time will be of the type vz z0 minus gt. This is a trivial problem. Suppose I, for a moment, switch off the gravitational field. So when I switch off the gravitational field, g, acceleration due to gravity, would become zero. If I switch off the gravitational field in the Lagrangian, g is put equal zero. So Lagrangian is independent of z coordinate. So what am I getting from Euler-Lagrange equation? d dt of the momentum along z direction, time derivative of momentum along z direction, if Lagrangian is independent of z coordinate, then time derivative of momentum component along z direction is zero, which means momentum along z direction is constant. That means momentum is conserved, which is what I have written. If L Lagrangian is independent of a certain coordinate z, then corresponding conjugate quantity, which is momentum, this is spatial coordinate, but the spatial coordinate and the momentum, they are the conjugate variable. The corresponding conjugate variable, which is momentum in that direction, is conserved. This is called Noether's theorem. Let me, I of course cannot resist the temptation of sharing with my students that this theorem was given by a German theoretical physicist, a lady, Emmy Noethers. And of course, uh, even in theoretical physics, in first half of 20th century, there were misogynistic people. So she was not, her contribution was not really recognized. But Einstein, when shifted to Princeton during Second World War time and joined the Institute of Advanced Learning, Emmy Noether came in contact with Einstein, and Einstein could realize the importance of this theorem. The theorem, put in very simple words, is just this, that if Lagrangian is independent of a certain coordinate x or y or z, then conjugate variable, which is momentum along either X or Y or Z direction will be conserved. If I extend it to plane polar system, and r and theta are variable, if Lagrangian is independent of theta, then corresponding conjugate variable will be angular momentum. So angular momentum will be conserved. Time and energy, they are conjugate of each other. So any Lagrangian independent of time implies energy conservation. A simple, very simple theorem, but states a very profound fact. With this, we come to the concept of generalized momentum. It is in the same slide. I have, let's say, n particles, Lagrangian, I have written down for these particles, and del del L, del xj dot is mxj dot, which is momentum component along z direction, momentum component of jth particle along x direction, and system has 3n minus k generalized coordinate qj. I think I have discussed it already. For n particle system, there are 3n coordinates to specify location of those n particles, and if k are the number of constrained equations, so 3n minus k will be the number of independent variables, and that is what are called the generalized coordinates. So in terms of generalized coordinates, in general, pj of momentum of the jth particle will be del L del qj dot, and if suppose L does not depend on particular parameter qk, Euler-Lagrange equation immediately gives me, if it does not depend on qk, del L del qk would be 0 in the Euler-Lagrange equation, which gives me ddt of del L del qk dot equals 0. Del L del qk dot is nothing but the momentum component, momentum pk. So p del dpk dt is 0, implying that general momentum pk, if Lagrangian is independent of qk, its conjugate generalized momentum pk will be conserved, will be a constant of motion. And such generalized coordinates of which Lagrangian is independent are ignorable or cyclic, they are referred to as cyclic coordinate. And this is our a general statement of profound theorem of Emmy Noether. With this, we go to 8th slide, which is numbered as S5. S5.
Is it fine?
Yeah, fine. So, from the definition, Pz equal del L del J dot, Py equal del L del Y dot, Px equal del L del X dot. I immediately get, after differentiation, which I really don't have to, because X dot is Vx, Y dot is Vy, velocity component, Z dot is Vz. I immediately get the momentum components as generalized momentum components, mbx plus qax, and similarly mby qa mbz qaz. Second term, first term of course is the usual momentum component, and second term in these expression is called potential momentum. With this, we go to a new problem, which is stated below in the same slide as 5. I have its diagram, corresponding diagram in the other slide, the subsequent slide. So I think I should go over to the next slide because we have also the diagram. So this slide is S6A. S6A. We have, as you can see in the diagram, a mass M2 hangs at one end of a string which passes over a frictionless non-rotating pulley, and at the other end of the string there is a non-rotating pulley of mass M1 over which these masses are capital M1 and capital M2. Over this non-rotating pulley of mass M1, there is a string carrying masses M1 and M2. I am to, for this system, I am to set up Lagrangian of the system, and I am to find acceleration of the mass. Well, I can see motion is taking place, say, along x direction. X direction is the vertical direction. A yz direction has no motion. So we have, in fact, for the equation of constraints, the strings are of fixed length. So one can, referring to the diagram, one can see capital X1 plus capital X2 equals some constant A, and small x1 plus small x2 equal another constant B. I have assumed the radii of the pulley to be much smaller compared to x1, x2 and capital X1, capital X2 and small x1, small x2. So differentiating, so these are our two generalized coordinates. Differentiating with respect to time, we get x2 dot equal minus x1 dot, x2 dot the lowercase minus x1 dot lowercase. So velocity of m1 is x1 dot, velocity of m2 is x2 dot equal minus x1 dot uppercase, of course, and velocity of m1 actually will be x1 dot plus x1 dot, this smaller uppercase time derivative of uppercase x1 and time derivative of lowercase x1. This follows from velocity addition formula. Similarly, velocity of mass m2 follows from the velocity of velocity addition formula. Therefore, kinetic energy could be written out of this entire system, could be written out as we have shown in equation 1. I believe up to this is absolutely clear to everybody. Then we go over to the next slide, which is numbered as S6B. S6B, yes. So kinetic energy part settled, potential energy is written down, which I have used simple MGH formula, and that gives me the Lagrangian, that is equation 3, which is very easy to get. So there's no explanation, I believe, needed. I go to slide 7A, slide 7A, and we write down the Euler-Lagrange equation with respect to the variables uppercase x1 and lowercase x1, and we find all these derivatives, and finally when we go to the slide S7B, with these equations I am able to find finally the downward acceleration. This is a just algebraic equation, linear equation, one can solve easily. So one has accelerations given in the last line by a slightly longish expression, m2 minus m1, m1 plus m2 minus 4, m1, m2, and so on, multiplied by g. So the problem essentially is simple. I go to slide S8, where in S8 where I solve problem 4 and I use cylindrical coordinate rho phi z. I write down the total kinetic energy. I write and I am to get only thing that he needs to understand is this force field in which particle is moving. That is the potential energy gradient giving me force. So potential energy itself is definable. That means the force field is conservative. So I am to find equation of motion in cylindrical coordinates rho phi z. So I have written down kinetic energy. I am sure all our students are familiar with mathematical physics, curvilinear chapter of curvilinear coordinates, where one had discussed cylindrical polar coordinates, spherical polar coordinates. So in cylindrical polar coordinates, kinetic energy will be as shown, and potential energy, of course, is function of rho, phi, and z. So I have L given by this relation, and I have written down Euler-Lagrange equation, which I was supposed to do for this case, which is simple differentiation. So I don't think it merits any explanation. Of course, after that, I go to S9, but I'm sorry, this is twin paradox, which I don't need to explain because anyway, this could be taken as some kind of notes for student. S9, twin paradox is very important. Important questions could be based on twin paradox, but I already have talked about and talked a lot about special theory of relativity, so I will not discuss it further. The paradox is dependent on time dilation formula. With that, I come to S10. S10. I discuss now the Hamilton's principle. So, in short, I consider a functional f x dot t. Function of a function is called functional. So, I consider, actually I've written function, should have written functional, because x is function of time and x dot velocity also is function of time. And I consider a line integral of this functional with two values of time as the upper and lower and upper limits, t1 and t2. So time integral of this functional is I, which I refer to say as 12.47. Hamilton's principle says that out of all possible paths, our system described by an appropriate functional will take on only such path for which this integral has a stationary value. Stationary value. And of course, if I go to the next slide, S11, I can see I have considered two paths here which are very close to our path across which the line integral to be calculated. So I come back to problem slide S10. I say that this functional has a stationary value relative to path differing infinitesimally from the correct function x equal xt, because at this, for this function, the functional has stationary value, and endpoints, end values of x at time t1 and t2 are x1 and x2, and paths, all paths have to, therefore, because you are taking integral from t1 to t2, so whichever path you adopt, will have to pass through points A1 and A2. Suppose xm is the path we see for which the functional has stationary value, then a possible set of varied paths would be given by xt equal xmt alpha nt. Alpha is some parameter, open parameter at the moment, could be done away with at the end of the calculation, and nt is a function of time which vanishes at t1 and t2. So with this condition, one is finding that at t1 and t2, uh, uh, x1 and x2 and your xn, all such paths will pass through the points a1 and a2, which correspond to time t1 and t2. So this is what I have shown in slide 11. We have a parametric family of curves, and integral is also a function of alpha. The way I have defined xt, how did I define xt? In the slide S10, I defined xt as xmt plus alpha times nt. In the slide S10, in the slide S10, S10, please S10. In the slide S10, I have defined xt as xmt plus alpha nt. Therefore, alpha is a parameter, essentially is open one. So I need to consider this. And with this, I go to slide number 12. Slide number 12. So function, slide number 12, not 13, slide number 12. So our integral as a function of alpha is t1 to t2, and x is function of t and alpha x dash, also is function of t alpha and t. So our functional f is function of a function and dt. And for stationarity across for the path x equal xmt, which corresponds to alpha equals 0, I should have the first derivative of this integral with respect to alpha at alpha equals 0 equal 0. Nt equal role of nt in the equation. Someone had asked, I just saw, go back to slide 10, role of nt I have uh, uh, edged or already mentioned in the last line. Nt is a function that vanishes at t1 and t2. So nt is any sort of function, but since your limits, upper limit, lower limit are, sorry, lower limit, upper limit are t1 and t2, the function nt needs to vanish at t1 and t2 in order that you have xmt, x1, t1, x2, t2, all of them pass through point a1, a2 of figure given in the slide S11. So I believe the question was, what was NT, is clear to everybody. So we come back to slide 12, and we differentiate for finding stationarity. We differentiate with respect to alpha. Ultimately, we put alpha equals 0. So upon differentiation, we get this quantity, and we integrate by parts the second term. So when we integrate by parts, I get what is shown below in the S12. Don't go to S13, please. S12. S12, yeah. After integration by parts, I get what is shown here. Integration by parts, I'm sure all of us are familiar with. Integral u if taken as first function, v taken as second function, then u times integral dv minus integral of integral dv, integral of v times derivative of u and integrated. So that is what I have done. And let us now go to the third slide, that is S13. So we have ultimately the derivative of I at alpha in the 13 as del f, del f del x minus del t of del f del x dash multiplied by nt equals 0. So if I take alpha equals 0 in the above equation, I get del f x, del f del x minus del t of del f del x dash at alpha equals 0, nt dt equals 0. Now, nt, as one of the students asked, is what? It is an arbitrary function. Since it is for any arbitrary function, the integral is 0 as shown in 12.55. Therefore, when I go to S14, I find that the integrand has to be 0. So, demanding stationarity condition of the integral, actually you can see effectively reduces to Euler-Lagrange equation or Euler-Lagrange differential equation. So this is what I have written. Delta of integral I equals 0 is valid when so-called Euler-Lagrange differential equation is valid. Now you may ask, what purpose is this serving? Purpose is this, that nature always is economical. Nature has to follow in various, in its evolutionary process, it has to follow a path for which certain quantity will have to be minimum. For example, if I am on the same medium, light ray will move from point A to point B, which will be a path of least time as well as least distance. But light ray as such follows path of least distance. So if I have two media of different refractive indices, a light ray from one medium enters into another medium. In that case, the path that light ray would follow certainly will not be a straight line. I think everyone can imagine this. It will be a path not of shortest distance, it will be a path of shortest time. So this principle, actually the Hamilton's principle, is simply making a generalization of the observations that I have made. So I have in the slide S15, I have summarized the Hamilton's principle. Motion of a dynamical system from time t1 to t2 will take place in such a fashion that the integral of Lagrangian in time, say from t1 to t2, will always have a stationary value. That means first derivative will be 0, and for local minimum, second derivative, of course, is what? Positive for minimum. And the quantity I, if I look at, is actually dimensionally what? Energy multiplied by time. Dimensionally energy multiplied by time. Energy multiplied by time is called action. And it action has, if I ask you, please name any quantity, I'm sure you know, at least one quantity which has the same dimension as action. Please name that quantity. Please name that quantity which has same dimensional form as action. Hello? No one replying.
Yes, sir.
Where we are replying,
Yes,
it
sir.
takes a lag of a minute before you hear
Okay,
our voice.
okay.
Yes, sir. What is it?
What I asked is, I have introduced presently a new quantity action, which probably they have not even heard of. This is energy multiplied by time. Integral is L into dt and integrated over T1 to T2. So integral I, which is called action, will have definitely dimension of energy into time. So please name yet another quantity which will have same dimension as that of action.
So they're saying Planck's constant. Somebody is saying power.
Planck's constant is good, very good. Planck's
Angular
constant
momentum.
or angular momentum. Actually, Planck's constant is quantum of angular momentum. So very right. So angular momentum. So action. So what is the what would now be the statement of action, the Hamilton's principle, that any system in nature, dynamical system, will evolve in time in such a fashion that the action integral of time should be stationary, minimum. And I think I have already explained with the help of light rays, particularly refraction, where light is going from one medium to another, not following shortest path. It is following path because light ray undergoes bending going from one medium to another. It follows, could be shown that it follows principle of least time. In optics, we call it as Fermat's principle, but anyway, it is a statement of this Hamilton's principle in a very specific case. With this, we go to the slide number 16, where slide number 16, I want to solve a problem. This is that with the help of Hamilton's principle, show in the case of conservative system. Conservative system, I am sure all of us know. For conservative system, force is given by negative gradient of potential energy. So in conservative system, mechanical energy will be conserved. All of us know. Like our gravitational force is conservative force. Our spring force is conservative force, because under the action of such forces, the mechanical energy of the spring or mechanical energy of a particle thrown in the vertically upward direction with certain velocity, mechanical energy remains conserved. And such things one has studied at the school level. So one can show with the Hamilton's principle that for a conservative system, 2 times T1, T2 kinetic energy integral is stationary for a dynamical path, and hence show that for single particle of mass m integral VDS is stationary, where s is the length of the arc of the particle trajectory. How do we show this? I have shown the solution here. Since I am talking about conservative system, therefore T plus V, kinetic energy plus potential energy, should be constant, or our Lagrangian being T minus V, it will become 2T minus C. C is constant. So integral T1 to T2 LDT will be naturally 2T dt T1 to T2 minus C times C being a constant, T2 minus T1. Since T2 minus T1 is a constant, it follows that if Hamilton's principle is true, then this integral 2 times kinetic energy integral from T1 to T2 should be stationary for a dynamical path. And kinetic energy of a single particle 2T is mb square, where and mb square, and v of course is ds upon dt. So v dt is ds. So the principle in effect then becomes integral mv ds taken along a actual dynamical path is stationary. I believe the solution to this problem is clear to everybody. We now go, because this is too trivial, so I go to slide number S17. This is a very famous problem. This is called Brachistochrone problem. Consider the path joining 2 points here, A and B, such that a mass starting from A slides on this path, and it takes least time in arriving at point B. It has to, because I already have stated nature is economical, friction is assumingly absent, and mass is moving entirely under the action of gravity, which is a conservative force. So I am to get the trajectory of this particle. What am I to get? The trajectory of this particle, and this is known as Brachistochrone problem. To solve this problem, as I have proceeded, we consider point A to be the origin. It doesn't matter, you can shift the origin. Point B to be with coordinates x0, y0. And the velocity at any arbitrary point xy under gravity will be square root of 2gy. And time taken along an arbitrary curve will be curve length ds upon velocity v, where velocity is given square root of 2gy, and ds is an elementary arc length along the curve. Now ds square in two-dimensional plane will be dx square plus dy square. Therefore ds will be square root of dx square plus dy square, and if I take dx common and y prime I denote by y prime dy dx, then I can write ds as 1 plus y prime square and square root of that dx. So therefore our time, which has, because I am to get trajectory of the particle for which time of travel is minimum. Time of travel is minimum. So integral is time, and that time is integral 0 to x0 ds by v. So I have put in ds, I have put in square root of 2gy, v and dx. So if I compare this with our functional, I find functional is actually a function of position coordinate, velocity coordinate, and time. So our functional by comparison here comes out to be 1 plus y prime square by y whole divided by y raised to the power half. So it is independent of time and it depends on y and y prime. And for t to be minimum, this integral to be minimum, as we have seen, the Euler-Lagrange equation has to be satisfied. So we have to satisfy this functional f has to satisfy the Euler-Lagrange equation ddx of df dy prime minus df dy equal 0. Now we go to S18. If
Sir,
I
how
have
many, sir, how many slides do you have more?
37th, I think we have 10, around 12, 13 more slides.
Yeah, so sir, actually we started sharp at 5 and we have been continuing. So students chat box is open. First of all, please write down. Can we continue for another 10-15 minutes
Yeah,
or what
I
is
would
it?
try to, I would try to wind up. I
Yeah,
would try to wind up.
yeah, yeah.
So,
Yes, they are
is,
saying yes. You please. I know some of you are tired, so sir will try to wind up, and the rest of the problems will be passed on to you if you have filled either of the two attendance, and also the Google form which was given today. So yes, sir, please try to wind up because sitting
yeah,
for
yeah.
3.5 hours is.
Yeah. So we have the slide number S17, and as I said, we have identified the functional and Euler-Lagrange equation that functional has to satisfy. And when the ddx of df dy prime is minus del f del y is 0, I can show that if in slide 18, S18, I can show f minus y prime df dy prime will be a constant. This is called Beltrami identity. And I have a slide giving a proof of Beltrami identity. So anyway, so I find that del f del y prime after differentiating with respect to y prime becomes what is shown in this slide. And I have substituted that into the Beltrami identity with the value or with the expression for f. And then I get 1 by square root of 2gy multiplied by 1 by square root of 1 plus, I'm sorry, there is a mistake, 1 plus y prime square, 1 plus y prime square equal a constant. And this could be parameterized, this equation, by a parameter theta, and it comes out to be the parameter theta, the parameterization with parameter theta shows that the curve y as a function of x is a cycloid. So a particle moving from point A to point B under gravity only in the absence of friction will have a path followed for minimum time. Path will be cycloid. In S19, show please S19, I have proved Beltrami identity. I have multiplied the uh, equation by del f del y del x and done something and finally shown f. One student can go through it. I think this is not a very difficult proposition. So I just ignore the proof. However, please don't ignore Beltrami identity. For all problems based on the Hamilton's principle, the Beltrami identity comes very handy in solving problems. You will definitely get problems from Hamilton's principle, and Beltrami identity is what? At least once you need to know how to get it. With this, we go to S20, where I have shown in the same medium shortest path joining 2 points in a homogeneous plane is a straight line. And in an inhomogeneous plane, of course, path follows Snell's law. I have mentioned it. I have identified the functional, and I need to show path is shortest. So I had taken distance d, and I had used Euler-Lagrange equation followed by Beltrami identity, which for the homogeneous medium gives a straight line, and as shown in the next uh, S21 for non-homogeneous medium, where we have introduced a quantity, a function gx, I get something like what I have shown, y prime gx is constant, and this could be identified because sin px, cos px are defined. So this could be identified as Snell's law. So I just now had stated that least the Hamilton's principle actually gives you the laws of reflection and refraction. So you indeed see that. And then we discussed in this problem, problem number 4, wherein I have taken a very important problem, I believe so. I have a particle moving under central force. Central force, I'm sure all of us know, a central force has to be in the radially inward, radially outward direction, and force has to be function of r with r cap of plus or minus sign. That is either radially inward or radially outward. So our gravity is a central force. So a planet moving under gravity with sun at one of the foci, that could be taken an example of such a problem, and I want to show that the orbit of the particle is an ellipse. So it is a very long calculation. In fact, we go to slide number 23. I identify the functional, and functional been identified, Euler-Lagrange equation been written, Beltrami identity applied, and then we go to slide number 24. The equation obtained after application of Beltrami identity is solved, and upon solving, we find equation satisfies. At the bottom, one can find equation 12.74 satisfies the solution r equal p divided by 1 plus e cos theta. This is equation of an ellipse with foci at O and E being the eccentricity of the ellipse. So this is a very long calculation. We have paucity of time. I am not explaining these steps, but
the students are getting really restive and their batteries are draining. So I humbly suggest that probably you have classes with us for EMT. One fine day you can take up these 4, 5, 10 slides, whatever are left today. So one day you can take up that at that time.
Yeah, sure. I think I have taken more than my quota of time.
Yes,
Of course,
if they are not listening, because if they are not listening, then that's not good.
There is no point actually.
Yes.
I would just be making babblement.
Yes, so I think, sir, it's better that the students are attentive, and it has been, they've really shown a patience of almost 4 hours by now, not just 3. So I think we should stop for today. However, these slides which are left, we can again have a discussion. So I advise I must thank you, Dr. Partha Goswami, for being so generous to have covered the theory as well as numericals for the students. We are announcing that this course is not here to revise your entire subject line by line. It is expected that you have gone through this syllabus and you are aware of these things, and through the perspective of an experienced teacher, you come to know where should you focus your attention upon. And because these are numerical problems, sir has been kind enough to show you what the theory is based upon, so that in case you have not come with completely revised status of this subject, it is not that you do not understand the classes. The theory part is covered here just to give you a guideline that this is the theory available in books, part of your syllabi, and now we must apply our brain to problems in physics based on these concepts. And the more and more problems you see, the more and more problems you get used to, and you become more and more adept at it. So that is really nice, sir. And even in EMT, focus is requested more on numerical problems with just brushing up of concepts. So the coming week is full of
Yeah,
EMT, statistical
but
mechanics.
actually it so happens that I find that the students are lacking in concept. So
Yes,
some
yes, sir. Yes, sir.
concept
Very
is
true.
has to be revised, then working out problems becomes a meaningful exercise.
Yes, yes, sir.
So
Definitely. Definitely, because every person is definitely not reading classical dynamics since morning. So if there are some equations right in front of our eyes, they really help a lot. So sir, can you please switch on your camera for 1 minute so that I can thank you? And
yeah,
I
yeah, yeah,
request Dr. Parul and Mansi to stop sharing now.
yeah.
Thank you so much, sir. So we shall have a class with you again on EMT, and where you would be covering some portion of EMT along with Dr. Rachna. Dr. Sanjay has already done polarization. So along with the organizing team, sir, thank you so much for
Yeah,
your
my
precious
pleasure.
time, attention, and all the effort.
No,
And
that's all right.
yeah,
I'm
I
serving
request,
students.
yeah, thank you, sir. I request Dr. Mansi and Parul to kindly share tomorrow's tomorrow's slide of lectures. Please
Ma'am,
do.
please wait for a minute.
Yeah,
I'm
yeah,
sharing.
yeah.
So
Students, you deserve compliments for all those who have stayed with us. Yes, I know it's long, but you see, if when you are attending lectures anywhere in the university or wherever, then also you have to have some sitting persistence, and you've already shown that you are capable of listening to long lectures. And now our advice is that all those who were attending today would be getting sir's PPT, which he has provided, the books he has provided, his recommendation about the books, and the list of the numericals he has provided for classical dynamics. So all that Dr. Partha Goswami has provided to us would be would be coming to you also. So tomorrow we'll have on third we will have electromagnetic theory by Sir, and then followed by a statistical mechanics lecture by Dr. Aditya Saxena, which will be also based on concepts plus theory. So the coming week is only electromagnetic theory and statistical mechanics. And they would
tomorrow,
request you,
ma'am, excuse me. Tomorrow, do I have class?
sir, you had asked for it.
No,
Dr. Mansi, can you
you
please
said
stop the recording now?
you would give.
Recording, not pause. Please stop the recording.